Preface of Mars and Its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. Mars and Its Canals by Percival Lowell, Director of the Observatory at Flagstaff, Arizona, non-resident professor of astronomy at the Massachusetts Institute of Technology, Fellow of the American Academy of Arts and Sciences, Membre de la Société Astronomique de France, Member of the Astronomical and Astrophysical Society of America, Mitglied der Astronomischen Gesellschaft, Membre de la Société Belge d'Astronomie, Honorary Member of the Sociedad Astronómica de Mexico, Janssen Medalist of the Société Astronomique de France, 1904, for researches on Mars, etc., etc. Preface. 11 years have elapsed since the writer's first work on Mars was published, in which were recorded the facts gleaned in his research up to that time, in which was set forth a theory of their explanation. Continued work in this interval has confirmed the conclusions there stated, sometimes in quite unexpected ways. 5 times during that period Mars has approached the Earth within suitable scanning distance and been subjected to careful and prolonged scrutiny. Familiarity with the subject, improved telescopic means, and long-continued training have all combined to increased efficiency in the procuring of data and to results which have been proportionate. A mass of new material has thus been collected, some of it along old lines, some of it in lines that are themselves new, and both have led to the same outcome. In addition to this pushing inquiry into advanced portions of the subject, study has been spent in investigation of the reality of the phenomena upon which so much is based, and in testing every theory which has been suggested to account for them. From diplopia to optical interference, each of these has been examined and found incompatible with the observations. The phenomena are all they have been stated to be, and more. Each step forward in observation has confirmed the genuineness of those that went before. To set forth science in a popular, that is, in a generally understandable form, is as obligatory as to present it in a more technical manner. If men are to benefit by it, it must be expressed to their comprehension. To do this should be feasible for him who is master of his subject and is both the best test of and the best training to that post. Especially vital is it that the exposition should be done at first hand, for to describe what a man has himself discovered comes as near as possible to making a reader the co-discoverer of it. Not only are thus escaped the mistaken glosses of second-hand knowledge, but an aroma of actuality, which cannot be filtered through another mind without sensible evaporation, clings to the account of the pioneer. Nor is it so hard to make any well-grasped matter comprehensible to a man of good general intelligence as is commonly supposed. The whole object of science is to synthesize and so simplify, and did we but know the uttermost of a subject, we could make it singularly clear. Meanwhile, technical phraseology, useful as shorthand to the colt, becomes meaningless jargon to the uninitiate, and is paraded most by the least profound. But still worse for the employ, symbols tend to fictitious understanding. Formulae are the anesthetics of thought, not its stimulants, and to make any one think is far better worth while than cramming him with ill-considered and therefore indigestible learning. Even to the technical student, a popular book, if well done, may yield most valuable results, for nothing in any branch of science is so little known as its articulation, how the skeleton of it is put together, and what may be the mode of attachment of its muscles. End of preface.
Chapter 1 of Mars and Its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adrian Stevens. Mars and Its Canals by Percival Lowell. Part 1. Natural Features. Mars and its Canals. Chapter 1. On Exploration. From time immemorial, travel and discovery have called with strange insistence to him who, wandering on the world, felt adventure in his veins. The leaving familiar sights and faces to push forth into the unknown has with magnetic force drawn the bold to great endeavour, and fired the thought of those who stayed at home. Spur to enterprise since man first was, this spirit has urged him over the habitable globe. Linked in part to mere matter of support, it led the more daring of the Aryans to quit the shade of their beech trees, reposeful as that umbrage may have been, and wander into Central Asia, so to perplex philologists into believing them to have originated there. It lured Columbus across the waste of waters, and caused his son to have carved upon his tomb that ringing couplet of which the simple grandeur still stirs the blood. A Castilla y a León, Nuevo Mundo dio Colón. To Castile and Leon, beyond the wave, another world Columbus gave. It drove the early voyagers into the heart of the vast wilderness, there to endure all hardship, so that they might come where their kind has never stood before, and now it points man to the pole. Something of the selfsame spirit finds a farther field today, outside the confines of our traversable earth. Science, which has caused the world to shrink and dwindle, has been no less busy bringing near what in the past seemed inaccessibly remote. Beyond our earth, man's penetration has found it possible to pierce, and in its widening circle of research has latterly been made aware of another world of strange enticement across the depths of space. Planetary distances, not mundane ones, are here concerned, and the globe to be explored, though akin to, is yet very different from our own. This other world is the planet Mars. Sundered from us by the ocean of ether, a fellow member of our own community of matter there makes its circuit of the sun, upon whose face features show which stamp it is as cognate to that on which we live. In spite of the millions of miles of intervening matterless void, upon it markings can be made out that distantly resemble our Earth's topography, and grow increasingly suggestive as vision shapes them better, and yet, among the seemingly familiar, reveal aspects which are completely strange. But more than this, over the face of it sweep changes that show it to be not a dead but a living world, like ours in this, and luring curiosity by details unknown here to further exploration of its unfamiliar ground. To observe Mars is to embark upon this enterprise, not in body but in mind. Though parted by a gulf more impassable than any sea, the telescope lets us traverse what otherwise had been barred, and lands us at last above the shores we went forth to seek. Real the journey is, though incorporeal in kind. Since the seeing strange sights is the essence of all far wanderings, it is as truly travel, so the eye arrive as if the body kept it company. Indeed, sight is our only far viatic sense. Touch and taste both hang on contact, smell stands indebted to the near, and even hearing waits on ponderable matter. Where sound soon dissipates away, only sight soars untrammelled of the grosser adjunct of the flesh, to penetrate what were otherwise unfathomable space. What the voyager thus finds himself envisaging shares by that very fact in the expansion of the sense that brought him there. No longer tied by means of transport to seas his sails may compass, or lands his feet may tread, the traveller reaches a goal removed in kind from his own habitat. He proves to have adventured not into unknown parts of a known world, but into one new to him in its entirety. In extent alone he surveys what dwarfs the explorer's conquests on earth, but size is the least of the surprises there in store for him. What confronts his gaze finds commonly no counterpart on earth. His previous knowledge stands him in scant stead, for he faces what is so removed from everyday experience that analogy no longer offers itself with safety as a guide. He must build up new conceptions from fresh data, and slowly proceed to deduce the meaning they may contain. Science alone can help him to interpretation of what he finds, and above all must he wean himself from human prejudice and earthbound limitation. For he deals here with ultra-mundane things, with just enough of cosmogony in common to make decipherment not despairable. This world is yet so different from the one he personally knows as to whet curiosity at every turn. He is permitted to perceive what piques inquiry, and by patient adding of point to point promises at last a rational result. Like mundane exploration, it is arduous too. Ad astra per aspera is here literally true, for it is a journey not devoid of hardship and discomfort by the way. Its starting point preludes as much. To get conditions proper for his work, the explorer must forego the haunts of men and even those terrestrial spots found by them most habitable. Astronomy now demands bodily abstraction of its devotee. Its deities are gods that veil themselves amid men-crowded marts, and impose withdrawal and seclusion for the prosecution of their cult, as much as any worshipped for other reason in more primeval times. To see into the beyond requires purity, in the medium now as formerly in the man, as little air as may be, and that only of the best is obligatory to his enterprise, and the securing it makes him perforce a hermit from his kind. He must abandon cities and forego plains. Only in places raised above and aloof from men can he profitably pursue his search, places where nature never meant him to dwell, and admonishes him of the fact by sundry hints of a more or less distressing character. To stand a mile and a half nearer the stars is not to stand immune. Thus it comes about that today, besides its temples erected in cities, monasteries in the wilds are being dedicated to astronomy, as in the past to faith, monasteries made to commune with its spirit, as temples are to communicate the letter of its law. Pioneers in such profession, those already in existence, are but the precursors of many yet to come, as science shall more and more recognise their need. Advance in knowledge demands what they alone can give. Primitive, too, they must be, as befits the still austere sincerity of a cult, in which the simplest structures are found to be the best. Still, the very wildness of the life their devotee is forced to lead has in it a certain fitness for his post in its primeval detachment from the too earthbound, in concept as in circumstance. Withdrawn from contact with his kind, he is by that much raised above human prejudice and limitation. To sally forth into the untrod wilderness, in the cold and dark of a winter's small hours of the morning, with the snow feet deep upon the ground, and the frosty stars for mute companionship, is almost to forget one's self, a man for the solemn awe of one's surroundings. Fitting portal to communion with another world, it is through such avenue one enters on his quest, where the common and familiar no longer jostle the unknown and the strange. Nor is the stillness of the stars invaded when some long unearthly howl, like the wail of a lost soul, breaks the slumber of the Mesa forest, marking the prowling presence of a stray coyote. Gone as it came, it dies in the distance on the air that gave it birth, and the gloom of the pines swallows up one's vain peering after something palpable, their tops alone decipherable in dark silhouette against the sky. From amid surroundings that, for their height and their intenancy, fringe the absolute silence of space, the observer must set forth who purposes to cross it to another planetary world. But the isolation of his journey is not always so forbidding. His coming back is no less girt with grandeur of a different though equally detached kind. Even before the stars begin to dim in warning to him to return, a faint suffusion as of half-suspected light creeps into the border of the eastern sky. Against it, along the far pine-clad horizon, mesa after mesa in shaggy lines of sentineling earth stands forth dark-marshalled in the gloom, informed with the prescience of what is soon to come. Imperceptibly the pallor grows, blanching the face of night, and one by one extinguishing the stars. Slowly then it takes on colour, tinging ever so faintly to a flush that swells and deepens as the minutes pass. One had said the sky lay dreaming of the sun in pale imagery at first that gathers force and feeling till the dreamer turns thus rosy red in slumbering supposition of reality. Then the blush dies out, the crimson fades to pink, the pink to ashes. The stars have disappeared, and yet it is not day. It is the supreme moment of the dawn, the hush with which the earth awaits its full awakening, for now again the colour gathers in the east, not with the impalpable suffusion it had before, but nearer and more vivid. No longer reflectively remote, rays imminent of the sun strike the upper air, the most adventurously refrangible turning the underside of a few stray clouds into flame-hued bars of glowing metal. They burn thus in the silent east, first red, then orange, and then gold, each spectral tint in prismatic revelation coming to join the next, till a sudden blinding burst of splendour, the solar disk tops the horizon's rim. Not less impressive is the journey when the afternoon watch has replaced the morning vigil by the drawing of the planet nearer to the sun. Lost in the brilliance of the dazzling sky, the planet lies hid from the senses' search. The quest were hopeless did not the mind guide the telescope to its goal. To theory alone it is visible still, and so to its predicted place the observer sets his circles, and punctual to the prophecy the planet swings into the field of view. One must be dulled by long routine to such mastery of mind not to have the act itself clothed with a sense of charmed withdrawal, the object of his quest. So much and more there are of traveller's glimpses by the way, compensation that offsets the frequent discomfort, and even balking of his purpose by inopportune cloud. For the best of places is not perfect, and a storm will sometimes rob him of a region he wished to see. He must learn to wait upon his opportunities, and then no less to wait for mankind's acceptance of his results, for in common with most explorers he will encounter on his return that final penalty of penetration, the certainty at first of being disbelieved. In such respects he will be even worse off than were the other-world discoverers of the 15th and 16th centuries, for they at least could offer material proof of things they had seen. Dumb Indians and gold spoke more convincingly than the lips of the great navigators. To astronomy, too, that other world was due. Without a knowledge of the earth's shape and size, got from Francisco of Pisa, Columbus had never adventured himself upon the deep. But more than this, an astronomer it was, in the person of Americus Vespucius, who first discovered the New World. By recognizing it as such, Columbus never dreaming he had lighted upon a world that was new, nor does it impair one jot or tittle of his glory that he knew it not. Nothing can deprive him of the imperishable fame of launching forth into the void in hope of a beyond, though he found not what he sought, but something stranger still. So, curiously, has it been with the Trans-Etherian. To Schiaparelli, the Republic of Science owes a new and vast domain. His genius first detected those strange new markings on the Martian disk, which have proved the portal to all that has since been seen, and his courage in the face of universal condemnation led to exploration of them. He made there voyage after voyage, much as Columbus did on earth, with even less of recognition from home. As with Columbus, too, the full import of his great discovery lay hid even to him, and only by discoveries since is gradually resulting in recognition of another sentient world. End of Chapter 1. Chapter 2 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adrian Stevens. Mars and its Canals by Percival Lowell. Chapter 2. A Departure Point. As the character of the travel is distinctive, so the outcome of the voyage is unique. If he choose his departure point aright, the observer will be vouchsafed an experience without parallel on earth. To select this setting out station is the first step in the journey upon which everything depends, for it is essential to a visual arrival that a departure point be taken where definition is at its best. Now, so far as our present knowledge goes, the conditions most conducive to good seeing turn out to lie in one or other of the two great desert belts that girdle the globe. Many of us are unaware of the existence of such belts, and yet they are among the most striking features of physical geography. Could we get off our globe and view it from without, we should mark two sash-like bands of country to the poleward side of either tropic, where the surface itself lay patently exposed. Unclothed of verdure themselves, they would stand forth doubly clear by contrast, for elsewhere cloud would hide to a greater or less extent the actual configuration of the earth's topography to an observer scanning it from space. One of these sash-like belts of desert runs through southern California, Arizona, New Mexico, the Sahara, Arabia Petraea, and the desert of Gobi. The other traverses Peru, the southern African veldt, and western Australia. They are desert because in them rain is rare, and even clouds seldom form. In a twofold way they conduce to astronomic ends. Absence of rain makes primarily for clear skies, and secondarily for steady air, and the one of these conditions is no less vital to sight than the other. Water vapour is a great upsetter of atmospheric equilibrium, and commotion in the air the spoiler of definition. Thus, from the cloudlessness of their skies, man finds in them most chance of uninterrupted communion with the stars, while by suitably choosing the spot he here obtains, as well that prime desideratum for planetary work, as near a heavenly equanimity in the air currents over his head as is practically possible. From the fact that these regions are desert, they are less frequented of man, and the observer is thus perforce isolated by the nature of the case, the regions best adapted to mankind being the least suited to astronomic observations. In addition to what nature has thus done in the matter, humanity has further differentiated the two classes of sights by processes of its own contriving. Not only is civilized man actively engaged in defacing such part of the earth's surface as he comes in contact with, he is equally busy blotting out his sky. In the latter uncommendable pursuit he has in the last quarter of a century made surprising progress. With a success only too undesirable, his habitat has gradually become canopied by a welkin of his own fashioning, which has rendered it largely unfit for the more delicate kinds of astronomic work. Smoke from multiplying factories, by rising into the air and forming the nucleus about which cloud collects, has joined with electric lighting to help put out the stars. These concomitants of advancing civilization have succeeded above the dreams of the most earth-centred in shutting off sight of the beyond, so that today few city-bred children have any conception of the glories of the heavens, which made of the Chaldean shepherds astronomers in spite of themselves. The old world and the new are alike affected by such obliteration. Long ago London took the lead with fogs proverbial, wholly due to smoke, fine particles of solid matter in suspension making these points of condensation about which water vapour gathers to form cloud. With the increase of smoke-emitting chimneys over the world, other centres of population have followed suit, till today Europe and eastern North America vie with each other as to which sky shall be the most obliterate. Even when the obscuration is not patent to the layman, it is evident to the meteorologist or astronomer. By a certain dimming of the blue, smoke or dust reveals its presence high up aloft, as telltalely as if the thing itself were visible. Some time since the writer had occasion to traverse Germany in summer from Göttingen to Cologne, and in doing so was impressed by a cloudiness of the sky he felt sure had not existed when he knew it as a boy. For the change was too startling and extensive to be wholly laid to the score of the brighter remembrances of youth. On reaching Cologne he mentioned his suspicion to Klein, only to find his own inference corroborated, observations made 20 years ago being impracticable today. 2 years later in Milan, Chiloria told the same story, the study of Mars having ceased to be possible there for like cause. Factory smoke and electric lights had combined to veil the planet at about the time Schiaparelli gave up his observations because of failing sight. With a certain poetic fitness, the sky had itself been blotted, just as the time the master's eyes had dimmed. America is not behind in this race for sky extinction. In the neighbourhood of its great cities and spreading into the country round about, the heavens have ceased to be favourable to research. Not till we pass beyond the Missouri do the stars shine out as they shone before the white man came. Few astronomers even fully appreciate how much this means, so used does man get to slowly changing conditions. It amounts indeed between Washington and Arizona to a whole magnitude in the stars which may be seen. At the Naval Observatory of the former, 64 stars were mapped in a region where, with a slightly smaller glass, 172 were charted at Flagstaff. Besides their immediate use as observing stations, these desert belts possessed immediate interest on their own account in a branch of the very study their cloudlessness helps to promote, the branch here considered, the study of the planet Mars. They help explain what they permit to be visible. For in the physical history of the Earth's development, they are among the latest phenomena and mark the beginning of that stage of world evolution into which Mars is already well advanced. They are symptomatic of the passing of a terraqueous globe into a purely terrestrial one. Desertism, the state into which every planetary body must eventually come, and for which, therefore, it becomes necessary to coin a word, has there made its first appearance upon the earth. Standing as it does for the approach of age in planetary existence, it may be likened to the first grey hairs in man, or better still, it corresponds to early autumnal frost in the passage of the seasons. For the beginning to age in a planet means not decrepitude in its inhabitants, but the very maturing of this its fruit. Evolution of mind in its denizens continues long after desolation in their habitat has set in. Indeed, advance in brain power seriously develops only when material conditions cease to be bodily propitious, and the loss of corporeal facilities renders its acquisition necessary to life. The resemblance, distant but distinctive, of the climatic conditions necessary on Earth for the best scanning of Mars with those which prove to be actually existent on that other world has a bearing on the subject worth considerable attention. It helps directly to an understanding and interpretation of the Martian state of things. Though partial only, the features and traits of our arid zones are sufficiently like what prevails on Mars to make them, in some sort, exponent of physical conditions and action there. Much that is hard of appreciation in a low, humid land shows itself an everyday possibility in a high and dry one. The terrible necessity of water to all forms of life, animal or vegetal, so that in the simple thought of the aborigines rain is the only god worth great propitiation, upon the due observance of which everything depends, brings to one a deeper realization of what is really vital and what but accessory at best. One begins to conceive what must be the controlling principle of a world where water is only with difficulty to be had and rain unknown. But in addition to the fundamental importance of water, the relative irrelevancy of some other conditions usually deemed indispensable to organic existence there find illustration too. On the high plateau of northern Arizona and on the still higher volcanic cones that rise from them as a base into now disintegrating peaks, the thin cold air proves no bar to life. To the fauna there, air is a very secondary consideration to water, and because the latter is scarce in the lowlands and more abundant higher up, animals ascend after it, making their home at unusual elevations with no discomfort to themselves. Deer range to heights where the barometric pressure is but 3/5 that of their generic habitat. Bear do the like, the brown bear of Northern American sea level being here met with 2 miles above it. Nor is either animal a depauperate form. Man himself contrives to live in comfort and propagate his kind where at first he finds it hard to breathe. Nor are these valiant exceptions. As Merriam has ably shown in his account of the San Francisco Peak region for the Smithsonian Institution, a most interesting report, by the way, the other animals are equally adaptive to the zones of more northern latitudes on the American continent, zones paralleled in their flora and fauna by the zones of altitude up this peak. All which shows that paucity of air is nothing like the barrier to life we ordinarily suppose, and is not for an instant to be compared with dearth of water. If, in a comparatively short time, an animal or plant accustomed to 30 inches of barometric pressure can contrive to subsist sensibly unchanged at 18, it would be rash to set limits to what time may not do. And this the more for another instructive fact discovered in this region by Merriam, that the existence of a species was determined not by the mean temperature of its habitat, but by the maximum temperature during the time of procreation. A short warm season in summer alone decides whether the species shall survive and flourish. That it has afterward to hibernate for 6 months at a time does not in the least negative the result. That the point of departure should thus prove of twofold importance, speeding the observer on his journey, and furnishing him with a vade mecum on arrival, is as curious as opportune. Without such furtherance, to the bodily eye on the one hand, and the mind's eye on the other, the voyage were less conclusive in advent, and less satisfactory in attent. End of chapter 2. Chapter 3 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adrian Stevens. Mars and its Canals by Percival Lowell. Chapter 3. A bird's eye view of past Martian discovery. With Mars, discovery has from the start waited on a parent disk. To this end every optical advance has contributed from the time of Galileo's opera glass to the present day, for apparent distance stands determined by the size of the eye, but although it is the telescopic eye that has increased, not the distance that has diminished, the effect has been kin to being carried nearer the planet, and so to a scanning of its disk with constantly increasing particularity. Mankind has, to all intents and purposes, been journeying Marsward through the years. Any historic account of the planet, therefore, becomes a chronicle of seeming bodily approach. Perhaps no vivider way of making this evident, and at the same time no better preface to the present work, could be devised than by putting before the eye, in orderly succession, the maps of Mars made by the leading areographers of their day, since the planet first began to be charted 65 years ago. The procedure is as much as possible like standing at the telescope and seeing the phenomena steadily disclose. Seen thus in order, the facts speak for themselves. They show that from first to last, no doubt concerning what was seen existed in the minds of those competent to judge by systematic study of the planet at first hand, and furthermore from their mutual corroboration, that this confidence was well placed. For, far from there being any conflict of authorities in the case, those entitled to an opinion in the matter prove singularly at one. Beginning with Maedler in 1840, the gallery of such portraitures of the planet comprises those by Kaiser, Green, and Schiaparelli, continued since Schiaparelli's time by the earlier works of the present writer. To this list has been added one by Flammarion, which, though not solely from his own work, gives so just a representation of what was known at the date 1876 as to merit inclusion. The remarkable drawings of Dawes and the excellent ones of Lockyer in 1862 to 1864 were never combined into maps by the observers, and though the formers were so synthesized by Proctor in 1867, the result was conformed to what Proctor thought ought to be, and so is not really a transcript of the drawings themselves. Each of the maps presented marked in its day the point areography had reached, and each tells its own story better than any amount of text. They are all made upon Mercator's projection, and omit in consequence the circumpolar regions. The later ones give, too, only so much of the surface as was shown at the opposition they record, for Mars, being tipped now one way, now another, regards the Earth differently according to its orbital position. In comparing them, therefore, the equator must be taken for medial line. Mercator's projection has been the customary one for portraying Mars, except for such oppositions as chiefly disclose the Arctic pole. And this, too, with a certain poetic fitness, for it comes by right of priority to delineation of a new world, seeing that Mercator was the first to represent in a map the mundane new world in its entirety, by the rather important addition of North America to the southern continent already known, and to give the whole the title America, with Ame at the top of the map and Rica at the bottom. In looking at the maps, it is to be remembered that they are what we should call upside down, south standing at the top and north at the bottom. Inverted they show because this is the way the telescopic observer always sees the planet. The disk would seem unnatural to astronomers were it duly righted. Just the same do men in the southern hemisphere look at our own Earth topsy-turvy, according to our view, the sun being to the north of them and the cold to the south. Certain landmarks distinguishable in all the maps may serve for specific introduction. The V-shaped marking on the equator pointing to the north is the Syrtis Major, the first marking ever made out upon the planet, and drawn by the great Huygens in 1659. The isolated oval patch in latitude 26 degrees south is the Solis Lacus, the pupil of the eye of Mars, while the forked bay on the equator, discovered by Dawes, is the Sapius Sinus, the dividing ton of which is the Fastigium Arin, has been taken for the origin of longitudes on Mars. 12 maps go to make the series. They are as follows: 1. Map of Beer and Maedler, dated 1840. 2. Map of Kaiser, 1864. 3. Map of Flammarion, Resume, 1876. 4. Map of Green, 1877. 5. Map of Schiaparelli, 1877. 6. Map of Schiaparelli, 1879. 7. Map of Schiaparelli, 1881. 8. Map of Schiaparelli, 1884. 9. Map of Lowell, 1894. 10. Map of Lowell, 1896. 11. Map of Lowell, 1901. 12. Map of Lowell, 1905. If these maps be carefully compared, they will be found quite remarkably confirmatory each of its predecessor. To no one will their inter-resemblance seem more salient than to draftsmen themselves, for none know better how surprisingly, even when two men have the same thing under their very noses to copy, their two versions will differ. Judgment of position and of relative size is one cause of variation, focusing of the attention on different details another. What slight discrepancies affect the maps are traceable to these two human imperfections. Maps 4 and 5 make a case in point. It was to his new-found Canals that Schiaparelli gave heed to the neglect of a due toning of his map, while Green, less keen-eyed but more artistic, missed the delicate canaliform detail to make a speaking portraiture of the whole. Amid the remarkable continuity of progression here shown, in which each map will be seen to be at once a review and an advance, we may, nevertheless, distinguish three stages in the perception of the phenomena. Thus we may mark 1. A period of recognition of larger markings only, 1840 to 1877. 2. A period of detection of canals intersecting the bright regions or lands, 1877 to 1892. 3. A period of detection of canals traversing the seas and of oases scattered over the surface, 1892 to 1905. Each period is here represented by 4 charts, and each expresses the result of a more minute and intimate acquaintance with the disk than was possible to the one that went before. To realize, however, how accurate each was according to his lights, it is only necessary to have the seeing grow steadily better some evening as one observes. He will find himself recapitulating in his own person the course taken by discovery for all those who went before, and in the lapse of an hour live through the observational experience of 60 years in much the same way that the embryological growth of an individual repeats the development historically of the race. 2 verses of Ovid, which the poet puts into the mouth of Pythagoras, outline with something like prophetic utterance the special discoveries which mark the 3 periods apart. Ovid makes Pythagoras say of the then world, Vidi ego, quod fuerat quondam solidissima tellus esse fretum, vidi factus ex aequore terras. Ovid, Metamorphoses, 15, 262. Where once was solid ground I've seen a strait, lands I've seen made from out the sea. True as the verses are of earth, the poet could not have penned them otherwise had he meant to record the course of astronomic detection on Mars, for they sound like a presentiment of the facts. A surface thought at first to be part land, part water, the land next seen to be seamed with straits, and lastly the sea made out to be land. Such is the history of the subject, and words could not have summed it more succinctly. Vidi ego quod fuerat quondam solidissima tellus esse fretum rings like Schiaparelli's own announcement of the discovery of the canals. Indeed, I venture to believe he would have made it had he chanced to recall the verse. So, vide factus ex aequore terras tells what has since been learned of the character of the seas. Of the 3 periods, the first was that of the main or fundamental markings only. It came in with Beer and Mädler, the inaugurators of areography. That they planned and executed their survey with but a 4-inch glass shows that there is always room for genius at the top of any profession, and that instruments are not for everything in its instrumentality. Up to their day, the reality of the planet's features had been questioned by some people, in spite of having been certainly seen and drawn by Huygens and others. Beer and Mädler's labours proved them permanent facts beyond the possibility of dispute. The second period was the period of the discovery of the now famous canals, a new era in the study of Mars, opened by Schiaparelli in 1877. Unsuspicious of what he was to stumble on, he seized the then favourable opposition to make, as he put it, a geodetic survey of the planet's surface. He hoped this undertaking feasible to the accuracy of micrometric measurement. His hopes did not belie him. He found that it was possible to measure his positions with sufficient exactness to make a skeleton map on which to embody the markings in detail, and thus to give his map vertebrate support. But, in the course of his work, he became aware of hitherto unrecognized ligaments connecting the seas with one another. Instead of displaying a broad unity of face, the bright areas appeared to be but groundwork for streaks. The streaks traversed them in all directions, tessellating the continents into a tilework of islands. Such mosaic was not only new, but the fashion of the thing was of a new order or kind. Straits, however, Schiaparelli considered them and gave them the name canali, or channels. How unfamiliar and seemingly impossible the new detail was, is best evidenced by the prompt and unanimous disbelief with which it was met. Unmoved by the universal scepticism which rewarded what was to prove an epoch-making discovery, Schiaparelli went on, in the judgment of his critics, from bad to worse, for in 1879 he took up again his scrutiny of the planet, to the detecting of yet more particularity. He reobserved most of his old canals, and discovered half as many more, and as his map shows, he perceived an increased regularity in his lines. In 1881 to 1882 he attacked the planet again, and with results yet further out of the common. His lines were still there, with more beside. If they had looked strange before, they now appeared positively unnatural. Not content with a regularity which seemed to the sceptics to preclude their being facts, he must needs see them now in duplicate. To the eyes of disbelief, this was the crowning stroke of factitiousness. In consequence, no end of adverse criticism was heaped upon his observations by those who could not see, but, curiously enough, what did not attract attention, the blindness of the critics was as much mental as bodily, for they failed to perceive that the very unnaturalness which seemed to them to discredit his observations really proved their genuineness. His discoveries were so amazing that any change in strangeness simply went to confirm the universal scepticism and clouded logic. Yet, properly viewed, a pregnant deduction stands forth quite clearly on a study of the maps. On comparing maps 5, 6, and 7, an eye duly directed is struck by a difference in the aspect of the lines. In his first map, the canals are depicted simply as narrow, winding streaks, hardly even roughly regular, and by no means such departures from the plausible as to lie without the communicatory pale. Indeed, to a modern reader prepared beforehand for geometric instruction, they will probably appear no canals at all. Certainly the price of acceptance was not a large one to pay, but like that of the Sibylline books, it increased with putting off. What he offered the public in 1879 was much more dearly to be bought. The lines were straighter, narrower, and in every way less natural than they had seemed 2 years before. In 1881 to 1882 they progressed still more in unaccountability. They had now become regular rule and compass lines, as straight, as even, and as precise as any draftsman could wish, and quite what astronomic faith did not desire. Having thus donned the character, they never more put it off. Now this curious evolution in depiction points, rightly viewed, to an absence of design. It shows that Schiaparelli started with no preconceived idea on the subject. On the contrary, it is clear that he shared to begin with the prevailing hesitancy to accept anything out of the ordinary. Nor did he overcome his reluctance, except as by degrees he was compelled. For the canals did not change their characteristics from one opposition to another. The eye it was that learned to distinguish what it saw, and the brain made better report as it grew familiar with the messages sent it. In other words, it is patent from these successive maps that the geometric character of the canals was forced upon Schiaparelli by the things themselves, instead of being, as his critics took for granted, foisted on them by him. We have since seen the regularity of the canals so undeniably that we are not now in need of such inferential support to help us to the truth, but too late, as it is, to be of controversial moment, the deduction is none the less of some corroboratory force. With the third period enters what has been done since Schiaparelli's time, for that master was obliged, from failing sight, to close his work with the opposition of 1890. In 1892, W. H. Pickering at Arequipa was the chief observer of the planet and made two important discoveries. One was the detection of small round spots scattered over the surface of the planet and connected with the canal system. The other, the perception of what seemed to him more or less irregular lines traversing the Mare Erythraeum. Both were notable detections. The first set of phenomena he called lakes, the second river systems, sometimes schematically canals, but without committing himself to canaliform characteristics, as his drawings made clear. The same phenomena were seen at that opposition at the Lick by Schaeberle, Barnard, and others, and called streaks. These discoveries took from the Maria their supposed character of seas, a most important event in knowledge of Mars. The next advance was the detection at Flagstaff in 1894 of their canaliform characteristics by my then assistant Mr. Douglas, who in place of the irregular streaks and river systems of his predecessors found the seas to be crossed by lines as regular and as regularly connected as the canals in the light regions. To him they appeared broad and ill-defined, but so habitually did to him the canals in the light areas, while for directness and uniformity the one set showed as geometrically perfect as the other. All the dark Maria of the southern hemisphere he found to be laced with them, and that they formed a network over the dark regions, counterparting that over the light. Still more significant was the fact that their points of departure coincided with the points of arrival of the bright region canals, so that the two connected to form in its entirety a single system. After the publication of his results, Lowell Observatory Annals, Volume 1, 1895, Schiaparelli identified some of those in the Syrtis with what he had himself seen there in 1888. Memoria 6, 1899, though his own had not been sufficiently well seen of him to impress him as canals. Of other additions to our knowledge since made by the writer the present book treats, as also of the theory they originally suggested to him, and which his later observations have only gone to confirm. End of Chapter 3. Chapter 4 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adrian Stevens. Mars and its Canals by Percival Lowell. Chapter 4. The Polar Caps. Almost as soon as magnification gives Mars a disk, that disk shows markings, white spots crowning a globe spread with blue-green patches on an orange ground. The smallest telescope is capable of this far-off revelation, while with increased power the figure grows steadily more articulate and full. With a 2¼ inch glass, the writer saw them 35 years ago. After the assurance that markings exist, the next thing to arrest attention is that these markings move. The patches of colour first made out by the observer are shortly found by him to have shifted in place upon the planet. And this is not through a mistake on his part, but through method in their phenomena, for all do it alike. In orderly rotation the features make their appearance upon the body's right-hand limb in the telescopic image, travel across the central meridian of the disk, and vanish over its left-hand border. One follows another, each rising, culminating and setting in its turn under the observer's gaze. A constantly progressing panorama passes majestically before his sight, new objects replacing the old, with the march so steady and withal so swift that a few minutes will suffice to mark unmistakably the fact of such procession. But for all this ceaseless turning under his gaze, after a certain lapse of time it is evident that the same features are being shown him over again. With such recognition of recurrence comes the first advance towards acquaintance with the Martian world, for that is all their journeying, their configuration alters not. proves them permanent in place, part and parcel of the solid surface of that other globe. This surface, then, lies exposed to view, and by its turning shows itself subject, like our earth, to the vicissitudes of day and night. In such self-exposure, Mars differs from all the 4 great planets, Jupiter, Saturn, Uranus, and Neptune. Features indeed are apparent on the first 2 of these globes, and dimly on the other 2 as well, but they lack the stability of the Martian markings. They are forever exchanging place. In the case of Jupiter, what we see is undoubtedly a cloud envelope, through which occasional glimpses may possibly be caught of a chaotic nucleus below. With Saturn it is the same, and the evidence is that the like is true of Uranus and Neptune. What goes on under their great cloud canopies we can only surmise. With Mars, however, we are not left to imagination in the matter, but so far as our means permit, can actually observe what there takes place. Except for distance, which, through science, year by year grows less, it is as if we hovered above the planet in a balloon, with its various features spread out to our gaze below. Attention shows these areographic features to be on hand with punctual precision for their traverse of the disk once every 24 hours and 37 minutes. For over 200 years this has been the case. Their untiring revolutions have been watched so well that we know the time they take to the nicety of a couple of hundredths of a second. We thus become possessed of a knowledge of the length of the Martian day, and it is not a little interesting to find that it very closely counterparts in duration our own, being only 1/35 the longer of the 2. We also find from the course the markings pursue the axis about which they turn, and just as the period of the rotation tells us the length of the Martian day, so the tilt of the axis, taken in connection with the form of the orbit, determines the character of the Martian seasons. Here again we confront a curious resemblance in the circumstances of the 2 planets. For the tilt of the equator to the plane of the orbit is, with Mars, almost precisely what it is for the Earth. The more carefully the 2 are measured, the closer the similitude becomes. Sir William Herschel made the Martian 28 degrees. Schiaparelli reduced this to 25 degrees, and later determination by the writer puts it nearer 24 degrees. The latter is the one now adopted in the British Nautical Almanac for observers of the planet. This is a very close parallelism indeed, so that in general character of the Martian seasons are nearly the counterpoint of ours. In length, however, they differ. First, because the year of Mars is almost double the length of the terrestrial one, and secondly, because from the greater ellipticity of Mars's orbits, the seasons are more unequal than is the case with us, some being run through with great haste, others being lingered on a disproportionate time. It is usual on the earth to consider spring as the period from the vernal equinox, about March the 21st, to the summer solstice, about June the 20th, summer as lasting thence to the autumnal equinox, autumn from this latter date, about September 20th, to the winter solstice on December 21st, and winter from that point on to the next spring equinox again. On this division our seasons in the northern hemisphere last respectively spring 91 days, summer 92 days, autumn 92 days, and winter 90 days. On Mars these become, reckoned in our days, spring 199 days, summer 183 days, autumn 147 days, and winter 158 days. If we had counted them in Martian days, they would have totalled about 1/35 less in number each. In its days and seasons, then, Mars is wonderfully like the Earth, except for the length of the year. We should hardly know the difference in reckoning of time, could we some morning wake up there instead of here. Only in one really unimportant respect should we feel strange. In months we should find ourselves turned topsy-turvy. But lunations have nothing to do with climate, nor with the alternation between night and day, and in these 2 important respects we should certainly feel at home. Though the axis could be determined by the daily march of any marking, and thus the planet's tropic, temperate and polar regions marked out. The process is made easier by the presence of white patches covering the planet's poles, and known in consequence as the polar caps. It is from measures of the patches that the position of the Martian poles has actually been determined. These polar caps are exactly analogous in general position to those which bonnet our own Earth. They reproduce the appearance of the ice and snow of our Arctic and Antarctic regions seen from space in a very remarkable manner. In truth, they are things of note in more ways than one, and would claim precedence on many counts. Priority of recognition, however, alone entitles them to premier consideration. Among the very first of the discs detailed to be made out by man, they justly demand description first. With peculiar propriety, the polar caps have thus the pass. Not only do they stand first in order of visibility, but they prove to occupy a like position logically when it comes to an explanation of the planet's present physical state. It is not matter of hazard that the most evident of all the planet's markings should also be the most fundamental, the fountainhead from which everything else flows. It is of the essence of the planet's condition, and furnishes the key to its comprehension. The steps leading to this conclusion are as interesting as they are cogent. They start at the polar cap's visibility, for their size first riveted man's attention, and then attention at them disclosed that most vital of the characteristics of the planet's surface, change. Just as almost all of the features we note are permanent in place, showing that they belong to the surface, so are they all impermanent in character. Change is the only absolutely unchanging thing, except position, about the features the planet presents to view. It was, in the aspect of the polar caps, that this important fact first came to light. Not only did they thus initially instance a general law, they have turned out to make it, for by themselves changing they largely cause change in all the rest. But for a long time they alone exemplified its workings. To Sir William Herschel we owe the first study of their change in aspect. This eminent observer noted that their varying size was subject to a regular rhythmic wax and wane timed to the course of the seasons of the planet's year. The caps increased in the winter of their hemisphere and decreased in its summer, and being situate in opposite hemispheres, they did this alternately with pendulum-like precision. His observations were soon abundantly confirmed, for the phenomena take place upon a vast scale and are thus easy of recognition. At their maximum spread, the caps cover more than 100 times as much ground as when they have shrunk to their minimum. In the depth of winter, they stretch over much more than the polar zone, coming down to 60 degrees and even 50 degrees of latitude north or south, as the case may be, thence melting till by midsummer they span only 5 or 6 degrees across. In this they bear close analogue to the behaviour of our own. Ours would show not otherwise, were they viewed from the impersonal standpoint of space. Very little telescopic aid suffices to disclose the Martian polar phenomena in this their more salient characteristics, and convince an observer of their likeness to those of the earth. Anyone may note what is there going on by successive observations of the planet with a 3-inch glass, nor is the change by any means slow. A few days at the proper Martian season, or at most a couple of weeks, produces conspicuous and conclusive alterations in the size of these nightcaps of the planet's winter sleep. Resembling our own so well, they were early surmised to be of like constitution, and composed, therefore, of ice and snow. Plausible on its face, this view of them was generally adopted, and common sense has held to it ever since. It has encountered, of course, opposition, partly from the very proper conservatism, but chiefly from that earth-centred philosophy which has doubted most advances since Galileo's time, and carbonic acid has been put forward by this school of sceptics to take its place. We shall critically examine both objections, the latter first, because a certain physical fact enables us to dispose of it at once. In casual appearance there is not much to choose between the rival candidates of common sense and uncommon subtlety, water and frozen carbonic acid gas, both being suitably white and both going and coming with the temperature. But upon closer study in one point of behaviour the two substances act quite unalike, and had half the ingenuity been expended in testing the theory as in broaching it, this fact had come to light to the suggestors as it did upon examination to the writer, and had served as a touchstone in the case. At pressures of anything like 1 atmosphere or less, carbonic acid passes at once from the solid to gaseous state. Water, on the other hand, lingers in the intermediate state of a liquid. Now, as the Martian cap melts, it shows surrounded by a deep blue band which accompanies it in its retreat, shrinking to keep pace with the shrinkage in the cap. This is clearly the product of the disintegration, since it waits so studiously upon it. The substance composing the cap, then, does not pass instantaneously or anything like it from the solid to the gaseous condition. This badge of blue ribbon about the melting cap, therefore, conclusively shows that carbonic acid is not what we see, and leaves us with the only alternative we know of, water. End of chapter 4.
Section 6 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Mars and its Canals by Percival Lowell. Chapter 5. Behavior of the Polar Caps. Assured by physical properties that our visual appearances are quite capable of being what they seem, we pass to the phenomena of the cap itself. Like as are the polar caps of the two planets at first regard, upon further study, very noticeable differences soon disclose themselves between the earthly and the Martian ones, and these serve to give us our initial hint of a different state of things over there, from that with which we are conversant on Earth. To begin with, the limits between which they fluctuate are out of all proportion greater on Mars. It is not so much in their maxima that the ice sheets of the two planets vary. Our own polar caps are much larger than we think. Indeed, we live in them a good fraction of the time. Our winter snows are in truth nothing but part and parcel of the polar cap at that season. Now, in the northern hemisphere, snow covers the ground at sea level, more or less continuously, down to 50 degrees of latitude. It stretches thus far even on the western flanks of the continents, while in the middle of them, and on their eastern sides, it extends 10 degrees farther yet during the depth of winter, so that we have a polar cap which is then 90 degrees across. In our southern hemisphere, it is much the same 6 months later in the corresponding winter of its year. On Mars, at their winter maxima, the polar caps extend over a similar stretch of latitude. They do so, however, unequally. The southern one is considerably the larger. In 1903, 136 days after the winter solstice, in the Martian calendar, February 27, it came down in longitude 225 degrees to 44 degrees of latitude, and may be taken to have then measured 93 degrees across. In 1905, 121 days after the same solstice, it stretched in longitude 235 degrees to latitude 42 degrees, and 158 days later, in longitude 221 degrees to latitude 41 degrees. Values which, supposing it to have been round, imply for it a diameter on these occasions of 96 and 97 degrees. It was then February 20th and March 10th, respectively, of the Martian year. These determinations of its size, at the two oppositions, agree sufficiently well, considering the great tilt away from us of the South Pole at the time and the horizonward foreshortening of the edge of the snow. It seems from a consensus of the measures to have been some 5 degrees wider in 1903 than in 1905, which may mean a colder winter preceding the former date. The cap was still apparently without a dark contour in both years, showing that it had not yet begun to melt. Less has been learned of the northern cap. In 1896 through 1897, when it was similarly presented skirting the other rim of the disk, a gap occurred in the observations corresponding to time by Martian months between February 24th and March 22nd. On the former date, the cap came down only to latitude 55 degrees, in longitude 352 degrees, on the subsequent one, and for several days after. On the subsequent one, and for several days later, the latitude of the southern limit of the snow was such as to imply a breadth to it of about 80 degrees. The cap was now bordered by a dark line, proving that melting had already set in. It cannot, however, at its maximum, have covered much more country than this, in view of its lesser extent on February 24th. Fair as our knowledge now is of the dimensions of the Martian polar caps at their maxima, we have much more accurate information with regard to their minima, and this too was obtained much earlier. That we should have first known their smallest rather than their greatest extent with accuracy may appear surprising, exactly the opposite being our knowledge of our own. It is not, however, so surprising as it appears, inasmuch as it is an inevitable consequence of the planet's aspect with regard to the sun. When the tilt of the axis inclines one hemisphere toward the sun, that hemisphere's polar cap must melt and dwindle, while at the same time it is the one best seen, the other being turned away from the sun and therefore largely from us as well, so that even such part of the latter as is illumined lies low down toward the horizon of the disk, where a slight change of angle means a great difference in size. It has thus come about that both the south and the north polar caps have been repeatedly well seen and measured at their minimum, and the measures for different Martian years agree well with one another. For the northern cap, 6 degrees in diameter is about the least value to which it shrinks. The south one becomes even smaller, being usually not more than 5 degrees across, while in 1894 it actually vanished, a thing unprecedented. Its absence was detected by Douglas at Flagstaff, and shortly after the announcement of its disappearance, the fact was corroborated by Barnard at the Lick. The position the cap would have occupied was at the time better placed for observation in America than in Europe, inasmuch as the cap is eccentrically situated with regard to the geographic pole, and its center was then well on the side of the disk presented to us, while in Europe it was turned away. This, together with the fact that it undoubtedly came and went more than once about this time, accounts for its disappearance not having been recognized there, haze left by it having apparently been mistaken for the cap itself. On Earth, the minima are much larger. In the northern hemisphere, the line of perpetual snow, or pack ice, in longitude 50 degrees east runs about on the 80-degree parallel, including with it the southern end of Franz Joseph Land. Opposite this, in longitude 120 degrees west, above the North American continent, it reaches down lower still to 75 degrees, so that the cap is then from 20 to 30 degrees in diameter. In the southern hemisphere, it is even larger. In longitude 170 degrees west, the land was found by Ross to be under perpetual snow in latitude 72 degrees. Cook had reached, in longitude 107 degrees east, an impassable barrier of ice in latitude 70 degrees 23 minutes. The season was then midsummer, January 30th. So that we are perhaps justified in considering 71 degrees south as about the average limit of perpetual snow or paleocrystic ice. This would make the southern cap at its minimum 38 degrees across. Pack ice with open spots extends still farther north. The Pagoda in 1845 was stopped by impenetrable pack ice in south latitude 68 degrees, and the Challenger in 1874 encountered the pack in latitude 65 degrees on the 19th of February, which corresponds to our 19th of August, the time at which the sea should be most open. The limit of perpetual snow is thus lower in the southern than in the northern hemisphere. Here again, then, the two minima differ, but in the reverse way from what they do on Mars. From this we perceive that the variations in size of the caps are much more striking on Mars than on the Earth, and that these are due chiefly to the differences in the minima, the maxima not varying greatly. To explain these interesting diversities of behavior in the several polar caps, we shall have to go back a little in general physics in order to get a proper takeoff. It is a curious concomitant of the law of gravity that the amount of heat received by a planet in passing from any point of its path to a point diametrically opposite is always the same, no matter what the eccentricity of the orbit. Thus, a planet has as many calories falling upon it in traveling from its vernal equinox to its autumnal as from the autumnal to the vernal again, although the time taken in the one journey may be very different from that of the other. This is due to the fact that the angle swept over by the radius vector, that is, the imaginary bond between it and the sun, is at all points proportional to the amount of heat received, just as it is of the gravity undergone, the two forces radiating into space as the inverse square of the distance. Thus the heat received by a point, or a hemisphere, through any orbital angle is independent of the eccentricity of the orbit. But it is not independent of the axial tilt, for the force of the sun's rays is modified by their obliquity. The amount of heat received at any point in consequence of the tilt turns upon the position of the point, and for any hemisphere taken as a whole, it depends upon the degree to which the pole is tilted to the source of heat. In consequence of being more squarely presented to its beams, the hemisphere which is directed toward the sun and therefore is passing through its summer season gets far more insolation than that which is at the same time in the depth of its winter. For a tilt of 24 degrees, the present received value for the axis of Mars, the two hemispheres so circumstanced get amounts of heat respectively in the proportion of 63 to 37. But though the summer and winter insolation thus differ, they are the same for each hemisphere in turn. Consequently, the mere amount of heat received cannot be the cause of any differences detected between the respective maxima and minima of the two polar caps. If heat were a substance which could be stored up, instead of being a mode of motion, the effect produced would be in accordance with the quantity applied, and the two caps would behave alike. As it is, the total amount has very little to say in the matter. Not the amount of heat, but the manner in which this heat is made at home, is responsible for the difference we observe. Now, though the total account is the same in passing from the vernal to the autumnal equinox, as far from the autumnal to the vernal, the time during which it is received in either case varies from one hemisphere to the other. It is summer in the former, while it is winter in the latter, and the difference in the length of the two seasons due to the eccentricity of the orbit makes a vast difference in the result. Winter affects the maxima, summer the minima attained. Of those opposite variations presented to us by the two caps, the maxima, the one most difficult to detect, is the easiest to explain, for the difference in the maxima seems to be due to the surpassing length of the Antarctic night. Owing to the eccentricity of the orbital ellipse pursued by Mars and to the present position of the planet's solstices, the southern hemisphere is farther away from the sun during its winter, and is so for a longer time. The seasons are in length for the northern hemisphere: spring 199 days, summer 183 days, autumn 147 days, and winter 158 days, while for the southern hemisphere they are spring 147 days, summer 158 days, autumn 199 days, and winter 183 days. The Arctic polar night is thus 305 of our days long, the Antarctic 382. Thus, for 77 more days, then happens to its fellow, the southern pole never sees the sun. Now, since the total sunlight from equinox to equinox is the same in both hemispheres, its distribution by days must be different. In the southern hemisphere, the same amount is crowded into a smaller compass in the proportion of 305 to 382, that being the hemisphere's relative ratio of days. But since during winter the cap increases, there is a daily excess of accumulation over dissipation of snow, and each 24 hours must on the average add its tithe to the sum total. Since the northern days are the warmer, each adds less than do the southern ones, and furthermore there are fewer of them. On both these scores, the amount of the deposition about the northern pole should be less than about the southern one. Consequently, the snow sheet there should be the less extensive and show a relatively smaller maximum, which explains what we see. With the minima, the action is otherwise. Inasmuch as the greater heat received during the daylight hours by the southern hemisphere is exactly offset by the shortness of its season, it would seem at first as if there could be no difference in the total effect upon the two ice caps. But further consideration discloses a couple of factors which might and possibly do come in to qualify the action and account for the observed effect. One is that though the total amount of heat received is the same, the manner of its distribution differs in the two hemispheres. In the northern one, the time from vernal to autumnal equinox is 382 days against 305 in the southern. Consequently, the average daily heat is then 5/4 more intense in the southern hemisphere. Indeed, it is even greater than this and nearer 4/3, because the melting occurs chiefly in the spring and in the first 2 months of summer, when the contrast in length of seasons between the two hemispheres is at its greatest. Now, a few hotter days might well work more result than many colder ones, and this would be particularly true of Mars, where the mean temperature is probably none too much above the freezing point to start with. Ice consumes so much caloric in the process of turning into any other state, laying it by in the form of latent heat before it can turn into water, and then so much more before this water can be converted into steam, that a good deal has to be expended on it before getting any perceptible result. Once obtained, however, the heat is retained with like tenacity, so that the process works to double effect. If sufficient heat be received, the ice is first melted, then evaporated, and finally formed into a layer of humid air, the humidity of which keeps it warm. Dry air is unretentive of heat, moist air the opposite, and for the melting of the ice cap to proceed most effectively, the temperature that laps it about must be as high as possible and kept so as continuously as may be. In between days, it be allowed to fall too low at night, much caloric must needs be wasted in simply raising the ice again to the melting point. This a blanket of warm air tends to prevent, and this again is brought about by a few hot days rather than by many colder ones. It is not all the heat received that becomes effective, but the surplus heat above a certain point. The gain in continuity of action thus brought about is somewhat like that exhibited between the running of an express and an accommodation train. To reach its destination in a given time, the former requires far less power, because it does not have to get up speed again after each arrest. Thus, the whole effect in melting the snow would be greater upon that hemisphere whose summer happens to be the more intense. The greater swing in size of the cap most exposed to the effects of the eccentricity is then the necessary result of circumstances, when the precipitation is not too great to be nearly carried off by the subsequent dissipation. This is the state of things on Mars, and the second of the factors above referred to. On the Earth, as we have seen, the polar caps are somewhat larger, at their maximum, and very much so at their minimum. Now this is just what should happen were the precipitation increased. Suppose, for example, that the amount of precipitation were to increase, while the amount of summer melting remained the same. And this would be the case if the vapor in the air augmented for one cause or another, and the result of each fresh deposit was locked up in snow. After a certain point, the cap would grow in depth rather than in extension. The winter deposit would be thicker, but the summer evaporation would remain the same. Now, if this occurred, it is evident that the minimum size of the cap would increase, relatively much faster than the maximum, and furthermore, that the relative increase of the minimum in the two caps would be greatest for that which had seasons of extremes. The result we see in the case of the Earth. In the Arctic cap, where in consequences of the eccentricity of the orbit, the winter is shorter, the maximum is less than in the Antarctic, and this extra amount of precipitation cannot be wholly done away with in its intenser summer, so that the minimum too is greater there. We reach then this interesting conclusion. We find that eccentricity of orbit by itself not only causes no universal glaciation in the hemisphere, which we should incidentally suppose likely to show it, but actually produces the opposite result, in more than offsetting by summer proximity what winter distance brings about. To cause extensive glaciation, we must have, in addition to favorable eccentricity, a large precipitation. With these two factors combined, we get an ice age, but not otherwise. The result has an important bearing on geological glacial periods and their explanation. Once formed, an ice sheet cools everything about it and chills the climate of the hemisphere. It is a perpetual storehouse of cold. Mars has no such general glaciation in either hemisphere, and the absence of it, which is due to lesser precipitation, together with the clearness of its skies, accounts for the warmth which the surface exhibits, and which has been found so hard hitherto to interpret. Could our Earth but get rid of its oceans, we too might have temperate regions stretching to the poles. End of section 6.
Section 7 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Surbhi Anand. Mars and its Canals by Percival Lowell. Chapter 6. Polar expeditions exert an extreme attraction on certain minds, perhaps because they combine the maximum of hardship with the minimum of headway. Inconclusiveness certainly enables them to be constantly renewed, without loss either of purpose or prestige. The fact that the pole has never been trod by man constitutes the lodestone to such undertakings, and it continues to defy him only whets his endeavor the more. Except for the demonstration of the polar drift current, conceived of and then verified by Nansen, very little has been added by them to our knowledge of the globe. Nor is there specific reason to suppose that what they might add would be particularly vital. Nothing out of the way is suspected of the pole beyond the simple fact of being so positioned, yet, for their patent inconclusion, they continue to be sent in sublime superiority to failure. Martian polar expeditions, as undertaken by the astronomer, are the antipodes of these pleasingly perilous excursions in three important regards, which, if less appealing to the gallery, commend themselves to the philosopher. They involve comparatively little hardship. They have accomplished what they set out to do, and the knowledge they have gleaned has proved fundamental to an understanding of the present physical condition of the planet. The antithesis in pole pursuing between the two planets manifests itself at the threshold of the inquiry, in the relative feasibility with which the phenomena on Mars may be scanned. For, curiously enough, instead of being the pole and its surrounding paleocrystic ice which remains hidden on Mars, it is rather the extreme extent of its extension and the lowest latitudinal deposit of frost which lies shrouded in mystery. The difficulty there is not to see the pole, but to see in winter the regions from which our own expeditions set out. And this because the poles are well displayed to us at times which are neither few nor very far between, while favorable occasions for marking the edge of the caps when at their greatest have neither proved so numerous nor so favorable. The tilt of the planet's axis, when conveniently placed for human observation, has been the cause of the one drawback, the planet's meteorological condition in those latitudes at that season the reason for the other. What knowledge we have of the size of the caps in degrees upon the surface of the planet, at this Their extreme equatorward extension has been given in the last chapter. Their aspect at the time, together with what that aspect betokens, was not there touched upon. With it, therefore, and the peculiarities it presents to view, we shall begin our account of the cap's annual history. When first the hemisphere, the pole of which has for half a Martian year been turned away from the sun, begins to emerge from its long hibernation, the snow cap which covers it down even to temperate regions presents an undelimited expanse of white, the edges of which merge indistinguishably into the groundwork color of the regions round about. Of a dull opaque hue along its border, its contour is not sharp, but fades off in a fleecy fringe without hard and fast line of demarcation. Such notably was the aspect of the North Temperate Zone in 1896 when, tilted as it then was away from us into a mere northern horizon of the planet's limb, it showed, prior to the definite recognition of the North Polar Cap in August of that year, and such too was the look of the disk's southern edge both before and after the first certain detection of the southern cap in 1903 and 1905. Each was then in the depth of winter, for in Martian chronology the season corresponded in each at the time to what we know in our northern hemisphere as the latter part of February and the early part of March, and the appearance of the planet's surface in both was not unlike what we know at the same season in latitude 45 degrees. Indeed, there is reason to suppose bad weather there then, and the extreme fringe, from the pale tint it exhibited, to have been cloud rather than snow. It is quite in keeping with what we know on earth or can conceive of elsewhere that such aspect should characterize the cap at or near the attainment of its greatest development. Whether it were not yet quite arrived at this turning point of its career, or had but slightly passed it, a vagueness of outline would in either event proclaim the fact. For, were the frost still depositing, the cap's edge would show indefinite, and on the other hand, had it just begun to melt, evaporation would give it an undefined edge before the melting water had gathered in sufficient quantities to be itself noticeable. Its behavior subsequent to recognition bore out the inference from its aspect when it first appeared, while for many days prior to its coming unmistakably into view, it was impossible to say whether what was seen of the southern cap in 1903 and 1905 was cloud or snow. So even after it had definitely disclosed itself, it continued to play at odds with the observer, showing sharp at the edges one day it would appear, but hazily defined the next, thus clearly demonstrating itself to be at then unstable acme of its spread. Such a state of things we are only too familiar with in our own March weather, when after days of sunshine that have melted off the winter's white and fringed it with rivulets and awakening grass, a snowstorm falling upon it powders the ground again that was beginning to be bare, and at one stroke extends the domain of the snow while mystifying the actual limits it may be said to occupy. The same condition of things, then, is not unknown on Mars, and to fix the precise date of so wavering a phenomenon is not so much matter of difficult observation as of physical impossibility. Nor is the southern cap at this the height of its winter expansion confined strictly to its own proper limits. Faint extensions, now so connected with its main body as to form part and parcel of it, now so detached and dull of tint as to make the observer doubtful of the exact relationship, are generally to be seen attendant on it. Hellas in winter is much given to such questionable garb, and has in consequence been mistaken by more than one observer for the cap itself, appearing, as it does well upon the southern limb, and being often the only region to show white. Indeed, frost-bound as it then is, to consider it the polar cap, though possibly geographically incorrect, may climatologically be sustainable. Its northern extremity extends down to latitude 30°, a pretty low latitude for frost. Still, such equatorward extension is not without corroborating parallel. In 1903, at what was in Martian dates April 26, the whole of the region south of the Solis Lacus and the nectar showed white, with a whiteness which may as well have been hoar frost as cloud. Now, the nectar runs east and west in latitude 28°, so that in this instance too, it is possible that Arctic conditions knocked at the very doors of the tropics. Encroachment of the sort is equivalent to snow in Cairo, and permanent snow at that, not an occasional snow flurry, but something to linger on the ground and stay visible 60 millions of miles away. Knowledge of either cap in this, the midwinter of its year, has been a matter of the most recent oppositions of the planet. Up to within the last few years, our acquaintance with either cap was chiefly confined to the months, one might almost say the weeks, immediately surrounding the summer solstice of its respective hemisphere. The behavior of the caps during the rest of their career was largely unknown to us, from the very disadvantageous positions they occupied at the times the planet was nearest to the Earth. Beginning with 1894, however, our knowledge of both has been much extended by a proportionate extension of the period covered by the observations. It used to be thought impracticable to observe the planet far on either side of opposition. Now it is observed from as much as 4 months before that event to the same period after it. The result is a systematic series of observations which in many ways has given unexpected insight into Martian conditions. One of the benefits secured has been the lengthening of the period of study of the cap's career, a pushing of inquiry farther back into its spring history, and a longer lingering with it in its autumnal rebuilding. Yet, up to the very last opposition, a gap in its chronology still remained between February 25th and April 1st. The opposition of 1905 has bridged this hiatus and brought us down to the latter date, at which the melting of the cap begins in earnest. From this point, April 1 on, we have abundant evidence of the cap's behavior. Its career now for some time is one long chronicle of contraction. Like Balzac's Peau de Charin, it simply shrinks, giving out of its virtue in the process. The cap proceeds to dwindle almost under the observer's eye till, from an enormous white counterpane spread over all the polar and a large part of the temperate zone, its area contracts to but the veriest nightcap of what it was before. From 70° across it becomes 60, then 50, then 40, till by the middle of the Martian May it has become not more than 30° in diameter. During this time, from the moment the melting began in good earnest, the retreating white is girdled by a dark band of a blue tint, which keeps pace with the edge of the cap, shrinking as it shrinks, and diminishing in width as the volume of the melting decreases. After the melting has been for some time under way, and the cap has become permanently bordered by its dark blue band, a peculiar phenomena begins its appearance in the cap itself. This is its fission into one or more parts. The process begins by the appearance of dark rifts which, starting in from the cap's exterior, penetrate into its heart until at last they cleave it in two. Rifts have been seen by several observers and in both caps, and what is most suggestive, they always appear in the same places year after year. Sometimes oppositions elapse between their several detections, for they are not the least difficult of detail, but when they are caught, they prove to lie just where they did before. The permanency in place of the rifts, a characteristic true of them all, shows them to be of local habit. Thus, the rift of 1884 and 1897 reappeared again to another observer in the same position in 1901. They are therefore features of or directly dependent on the surface of the planet. But it will not do from this fact to infer that they are expressive of depressions there. The evidence is conclusive that great irregularities of surface do not exist on Mars. As we shall see when we come to consider the orology of the planet, it is certain that elevations there of over 2,000 or 3,000 feet in altitude are absent. Differences of temperature able to explain a melting of the ice in one locality coincidentally with its retention in an adjacent one must in consequence be unknown. And this much more conclusively than at first appears, for the reason that the smaller the planet's mass, the less rapidly does its blanket of air thin out in ascent above the surface. This is in consequence of the greater pull the larger body exerts and the greater density it imparts to a compressible gas like our atmosphere. Gravity acts like any force producing pressure, and by it the envelope of air is squeezed into a smaller compass. But as this is done throughout the atmospheric layer, it means a more rapid rarefaction as one leaves the body. The action is such that the height necessary to reach an analogic density varies inversely as the gravity of the mass. In consequence of this, to compass a relative thermometric fall for which a moderate difference of elevation would suffice on Earth, an immoderate one must be made on Mars, for gravity there being but 3/8 what it is here. 8/3 the rise must be made to attain a proportionate lowering of temperature. This fact renders the above argument against elevation and depression being the cause of the phenomena 3 times as cogent as it otherwise would be. With so gradual a gradient in barometric pressure there, and so low a set of contour lines, altitude must be a negligible factor in Martian surface meteorologic phenomena. Both density and temperature can be but little affected by such cause, and we must search elsewhere for explanation of what surface peculiarities we detect. Meanwhile, the rifts themselves, from being lines which penetrate the cap from its periphery in towards its center, end by traversing it in its entirety and separating portions which, becoming outlying subsidiary patches, themselves proceed to dwindle and eventually disappear. The rifts usually take their rise from such broader parts of the cap encircling blue belt as make beads upon that cordon and are clearly spots where the product of the melting of the cap is either specially collected or produces its most visible effect. So far, the description might apply with substantial accuracy to either cap, yet the conduct of the two is in some ways diverse and begins to accentuate itself from this point on. From the point that the North Pole cap reaches a diameter of about 25 degrees, a singular change steals over it. From having been up to then of a well-defined outline, it now proceeds to grow hazy and indistinct all along its edge. This change in its character, at the same period of his career, has been quite noticeable at each of the 3 last oppositions, so that small doubt remains that the metamorphosis is a regularly recurrent one in the history of the cap. Coincident with the obliteration of its contour, its dimensions seemingly enlarge. It is as if a hood had been drawn over the cap of a dull white, different from the dazzling brilliance of the cap itself and covering more ground. Such is probably what occurs with vapor for veil. The excessive melting of the cap produces an extensive evaporation, which then in part condenses to be deposited afresh, in part remains as a covering, shutting off from our view the outlines of the cap itself. It would seem that at this time the cap melts faster than the air can carry it off. A sort of steaming appears to be going on, taking place in situ, for it clearly is not wafted away. The time of its coming to is significant, for the season is May 15, the height of time for a spring haze to set in. Then later, it dissipates with the same quiet indefiniteness with which it gathered. It is sometime in Martian June before the spring haze clears away, and when it does go, only a tiny polar cap stands revealed beneath it from 6 to 8 degrees across, or from a tenth to a 15th of what it was when it passed into its curious spring chrysalis. The date of emergence varies. In 1903 it occurred early, the haze not being marked after June 3rd, though recurring again at intervals for a day or so. In 1905 it was later, perceptibly thin after June 21. It did not certainly clear away till June 9 and came back again on July 16 and possibly on the 25th. These vicissitudes of aspect give us glimpses into a sweet unreasonableness in Martian weather which makes it seem more akin to our own. And this on two counts, diurnal and annual. From day-to-day atmospheric conditions shift for purely local cause, while furthermore successive Martian years are not alike. In some, the season is early, in others late, so that Mars is no more exempt than are we from the wantonness of weather. Clearly disclosed, thus reduced to its smallest possible terms, it remains for some months of our days, for 6 weeks of its own. During that period, it continues practically unchanged, neither increasing nor decreasing significantly in size, nor altering notably in aspect. Measures of the drawings of it then make it from 5 to 8 degrees across, and it is possible that it really fluctuates between narrow limits, though its clear-cut outline at all times renders the variation difficult to explain. We are not so near it as we could wish, for on these occasions, even at their best, it is over 200 times as distant as the moon, and the greatest magnification possible still leaves it 100,000 miles away. To the South Polar Cap a somewhat similar history attaches, but with a difference. In its case, no such regularly recurrent spring haze has yet been noted. The melting of this cap would seem to be of a more orderly nature than its fellow, and not to outdo what can conveniently be carried off. That an excess of evaporation should not take place is the more peculiar from the fact that at its maximum it is the larger of the two, and therefore has the greater quantity of matter to get rid of. Its summer also is shorter than the Arctic one, so that it has the less time to dispose of its accumulations. The only other respect in which it seems to be differently circumstanced from its antipodes is in the character of its surroundings. About it are large blue-green areas which with intermissions stretch down in places to within less than 10 degrees of the equator, whereas the other pole is continuously encircled for long distances by practically uninterrupted ochre. The character of the environment seems thus the only thing that can account for the difference in behavior, and this proves the more plausible when we come to consider what these two classes of regions respectively represent. In other ways as well, the southern cap is the more self-contained. The rifts, indeed, break it up into separate portions, and these in part remain as outlying detachments of the main body, as was notably the case in 1877 and in 1894, but they hardly have the permanency and importance of those similarly formed about the Arctic pole. Nothing Antarctic, for instance, compares with the subsidiary patch of the North Polar regions lying in longitude 206 degrees, which both in Schiaparelli's time and during the late oppositions as well was almost as fixed a feature of the Arctic zone as the cap proper. Not quite so constant, however, and not so solid-looking a landmark is this patch for all its extent, which nearly equals the area of the more legitimate portion. It bears on its face a more pallid complexion, as if it were thinner, and this is borne out by the fact that it occasionally disappears, an event which so far at least has never befallen the northern cap itself. Less constant, the southern one is to its own minimum than the northern. In some seasons, in most in fact, it reaches like the other a more or less definite limit of diminution which it does not pass. But this is not always the case. In 1894, it disappeared entirely at the height of its midsummer. The season was probably unusually hot then in the southern hemisphere of Mars. In position, the caps have something to say about physiographic conditions. Both caps, at their minima, are then irregular, and the center of the south one is markedly eccentric to the areographic pole. It lies some 6 degrees north along the 30th meridian. The northern one is also probably eccentric, but much less so, with a divergence not much exceeding a degree and of doubtful orientation. Not only are both the caps not upon their respective poles, but they are not opposite each other, the one lying in longitude 30 degree, the other in 290 degree. This speaks, of course, for local action. In some wise, this must depend on the configuration of the surface, yet, so far as markings go, there is nothing to show what the dependence is. The eccentric of the caps is paralleled by the like state of things on Earth. The pole of cold does not coincide in either hemisphere with the geographic pole. On the Earth, its position is largely determined by the distribution of the land masses. Continents are not such equalizers of heat as oceans because of their conductivity on the one hand and their immobility on the other. In winter, they part with their heat more quickly, and convection currents cannot supply the loss. This accounting for thermal pole eccentricity is inapplicable to Mars because of the absence there of bodies of water. And it is significant that the degree the earthly poles of cold are out much exceeds what is the case on Mars. Possibly, areas of vegetation there replace to some effect areas of water. It is certainly in favor of this view that the Arctic regions there are more desert than the Antarctic, and that the North Pole of cold occupies more squarely the geographic pole. Not till 1903 did the actual starting again of either cap chance to be seen. Nor was this, indeed, a matter of hazard, but of persistent inquiry by observation, prolonged after the planet had got so far away that its scanning had hitherto been discontinued. Such search beyond the customary limits of observation was essential to success because of the relation of the axial tilt to the position of the planet in its orbit. At an opposition well placed for nearness, the tilt is such as largely to hide the pole and to present the polar regions too obliquely to view for effective scanning. This is true both of the Arctic and the Antarctic regions in turn, for the Martian axis, being inclined somewhat as our own is to plane of the planet's orbit, we at times see well and at times but poorly the Arctic or Antarctic zones. The cap, the starting to form of which was thus caught, was the Arctic one. The date 128 days after the northern summer solstice or thereabouts, for as is perhaps natural, the advent of the phenomenon partook of the wave-like advance of such things familiar on Earth, an advance succeeded by a recession and then followed by another advance. So much is proof of local weather there as here. Hoar frost was successively deposited and then melted off. What is significant, the deposition of the frost took place simultaneously over large areas. The very first patch of it, in about longitude 320 degrees, extended at one stroke down to latitude 55 degrees, for it actually crossed the Piraeus somewhat to the south. A second patch stretched to the east of the cap. Two wings these made to the kernel of cap itself. Through the wings could be marked the line of the canal, the Piraeus upon the one side, the Enipeus upon the other. Such visibility of the canals through the wide stretches proved the white not to be due to clouds suspended between us and them, but a surface deposit which found no lodgment upon the canals themselves. The same avoidance of dark markings was evidenced by the showing of the dark rim round the cap's kernel. Now, if the deposit were indeed hoar frost, this failure to find permanent foothold on the dark markings is what we should expect to witness, for whether they were vegetation or water, equally in either case the frost would melt from them first. Probably they were both vegetal, though some doubt might exist about the latter, the band around the kernel. It was then August 20 in that hemisphere. Such deposition over great stretches of country is perhaps not so surprising as it appears at first sight when seen from without in its totality. After all, something not unlike it occurs in our snowstorms when hundreds of square miles are whitened at once. Furthermore, with an atmosphere as thin as Mars seems to possess, the temperature must be perilously near the freezing point in the Arctic and subarctic regions at the close of summer. Steadily, with intermissions, the white sheet increased until even the dark border to the cap became obliterate, the kernel showing at first through the veil like the ghost of what it had been, and then ceasing to be visible at all, its delimitations being buried under deeper and deeper depositions of frost. The perennial portion of the cap was thus merged in the new fallen snow. This marked the oncoming of the Arctic winter in full force, and happened even before the polar sun had wholly set, for the pole did not enter into the shadow till 2 of our months later, the autumnal equinox occurring 183 days after the summer solstice, or 55 days after the first fall of frost. Then the pole passed into its star-strewn Arctic night, a polar night of twice the duration of our own, and the circumpolar regions entered upon their long hibernation of 10 of our months. End of section 7. Recording by Surbhi Anand.
Section 8 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Mars and its Canals by Percival Lowell. Chapter 7. White Spots. In addition to the polar caps proper and to the subsidiary polar patches that often in late summer flank them round about, other white spots may from time to time be seen upon the disk. In appearance, these differ in no respect, so far as observed, from the Arctic subsidiary snowfields. Of the same pure argent, they sparkle on occasion in like manner with the sheen of ice. Equally, with the polar caps, they remain permanent in place during the period of their visibility, and are themselves long-lived. Though by no means perpetual, their duration is reckoned by weeks and even months, and they recur with more or less persistency at successive Martian years. That, when seen, they show in particular positions apparently unaffected by diurnal change, precludes their being clouds, and this fact, taken in connection with the character of their habitat, is the puzzling point about them. For they affect chiefly the North Tropic belt. They, or at least their nuclei, are small, about 2 or 3 degrees in diameter, and are not particularly easy of detection as a rule, though certain larger ones are at times conspicuous. Chromatic rather than formal, definition is necessary to their bringing out, as is witnessed by the superb colours the disk presents at the times when they are best seen. It is then that Mars puts on the look of a fire opal. The first such spot to be noticed was one which Schiaparelli detected in 1879 at the second opposition in which he studied the planet. He called it the Nix Olympica, showing that he recognized in it a cousin ship to the polar snows. Yet it lay in latitude 20 degrees north, longitude 131 degrees, in the midst of the ochre stretches of that part of the disk. It was a small roundish white speck of not more than 2/3 the diameter of the polar cap. Reseen by him in 1881, it failed to appear at subsequent oppositions and was not caught again until 1888. Then once more it vanished, not to be detected anew till many years after at Flagstaff, coming out rather surprisingly in 1903. It showed, however, in the same place as before, so that its position, but not its existence, is permanent. A similar but smaller patch was apparent to Schiaparelli at the same opposition of 1879. This one, which he styled the Nix Atlantica, lay between the Thoth and the Syrtis Major. It was about half the size of the Nix Olympica, and has never since been seen, though it should have been had it continued to be what it then was. On the other hand, phenomena of the sort undetected of Schiaparelli have been remarked at Flagstaff. On May 18, 1901, I was suddenly struck by the singular whiteness of the southeast corner of the Elysium, where that region bordered the Trivium. Elysium has a way of being bright, but not with such startling intensity as this spot presented, nor in so restricted an area as was here the case. The spot was so much whiter than anything I had ever previously seen outside the polar caps that it arrested my attention at once, and this the more that I had observed this same part of the planet the day before and perceived nothing out of the ordinary. Once detected, however, the spot continued visible. The next day it was there with equal conspicuousness, and now thrust an arm across the Cerberus, entirely obliterating the canal for the space of several degrees. In this salience it remained day after day till the region passed from sight, to reappear with it 6 weeks later, when the region again rounded into view. The hour of the Martian day seemed to make no difference in its visibility. It was seen from early morning till Martian afternoon, as late as the phase permitted. Clearly there was nothing diurnal about its revealing, and it lasted for at least 3 months and a half, until the planet got so far away that observations were discontinued. It was to all appearances an intense snow, but now comes the singular fact about it. It lay within 10 degrees of the equator, and showed from the end of June to the latter part of August. To our ideas there could be no more inopportune place or time for such an exhibition, for it cannot have been due to a snow-capped peak, as we know for certain that there are no mountains in this or in any other part of the planet. Besides, it had not appeared in previous Martian years, which it infallibly would have done had it been a peak. Indeed, it baffles explanation beyond any Martian phenomenon known to me. It seems directly to contradict every other detail presented by the disk. The phenomenon is thus unique in kind. It is not, however, unique as a specimen of its kind. The eastern coast of Aeria, where that region borders the Syrtis Major, is prone to a brilliance of the same sort. It is a narrow belt of country that shows thus, nothing but the coastline itself, but this for a considerable distance, stretching several hundred miles in length. It has stood out saliently bright now at every opposition which I have observed, beginning with 1894. Sometimes it has been described in the notes as bright simply, sometimes as white, and once, in 1901, as glistening at one point like ice. Yet, when upon the terminator, it has never stood forth as a mountain range should have done to declare its character. It has been evident regardless, apparently, of the Martian season. In 1894 it was bright from October the 25th to January the 16th, Martian chronology. In 1896 from December the 22nd to January the 7th. In 1901 from July the 13th to the 15th. In 1903 at about the same date, and so in 1905. It was whitest during the latter oppositions, showing that the effect is most marked in its midsummer. All of the above instances of extrapolar white have been located within the tropics. Examples of the same thing, however, occur in the north temperate zone. Tempe, a region just to the west of the Mare Acidalium, is exceedingly given to showing a small white spot close upon the mare's border in latitude 50 degrees north. This spot too on occasion glitters, as it were with ice. It is also at times very small, so that whereas much of Tempe is by nature bright, but a small kernel of it is dazzling. The list might be easily extended from the record book. Thus on March the 1st and 2nd, 1903, the disk showed speckled with minute white spots, one in Arcadia in latitude 41 degrees north, one in Tharsis near the equator, a third just north of the Phoenix Lucus in 10 degrees south, and a fourth, the Nix Olympica, and on April the 11th a glittering pinpoint starred like a diamond in the centre of the Pons Hectoris. On both these occasions the Martian season was summer, July the 9th for the latter, June the 21st for the former date. As one approaches the North Pole, spots of like character become more numerous, especially are such visible north of the Mare Acidalium in the Arctic region thereabout, from 63 degrees to 75 degrees north. From so widespread a set of instances, the only explanation which seems to fit the phenomena is that the mean temperature of Mars is low, not very much above freezing, and that whatever causes a local fall in the temperature results in hoarfrost. Such an explanation accords well with the distance of the planet from the Sun and the thinness of its atmosphere. At the same time, it shows that the mean temperature over the greater part of the planet, the greater part of the time, is above the freezing point, and that consequently it is no bar to vegetation of a suitable sort. That the hoarfrost should be found, even at the equator, may perhaps be due to the very thinness of the air covering of Mars, which would tend to make the actual insolation more of a factor than it is with us, and by the great length of the Martian seasons. In midsummer, the greatest insolation occurs in the Arctic and temperate, not in the tropic regions. On the other hand, an atmosphere tends to accumulate heat for the tropics. With us the latter factor is prepotent. It would be less effective on Mars. Then again, the double duration of summer would tend to emphasize insolation as the important factor in the matter. But it is possible that greater deposition plays a part in the matter. On Earth the rainfall is greatest near the equator, and something of the sort may be true of the zones of moisture on Mars. That the most striking spots are found to the west of large dark areas may in this connection have a meaning, inasmuch as, such regions being vegetation covered, the air over them is probably more moisture laden. One point about the position of the spots is of moment. They have all been found in the northern hemisphere, or within 10 degrees of it in the southern equatorial region. This seems at first a question of hemispheres, but when we consider that the light areas of the surface are chiefly in the boreal hemisphere and in the south tropic belt, we perceive that it may be rather the character of the surface there than the particular hemisphere in the abstract that is decisive in the matter. Nevertheless, the austral hemisphere is the hemisphere of extremes, possessing a shorter, hotter summer and a longer, colder winter than its antipodes. This would not favour sporadic, small depositions of frost in summer so much as would a climate of a more mean temperature. From the relative lack of atmospheric covering over the planet, we should expect the nights to prove decidedly cool, while the days were fairly warm. Of this we have perhaps evidence in a singular aspect shown by the Mare Acidalium in June 1903. The account of it in the Annals reads thus: On May the 22nd an interesting and curious phenomenon presented itself. On that day, so soon as the Mare Acidalium had well rounded the terminator onto the disk, at 352 degrees longitude, the whole of its central part showed white, the edges of the marking alone remaining as a shell to this brilliant core. So striking was the effect that beside appearing in the drawing it found echo in the notes. The next day no mention is made of it, and a drawing made under 20 degrees longitude shows the Mare as usual and the bright spot in Tempe in its customary place. Neither was anything of the sort noticed on the 24th and 25th, but on the 26th, the day of the projection upon the terminator, the effect of the 23rd reappeared, the longitude of the centre being 332 degrees. Fortunately on that day a further drawing was secured, which enabled its subsequent behaviour to be followed. Made 3 hours later than the other, the longitude of the centre being 13 degrees, this drawing shows the Mare well on the disk, its whole area as dark as usual, and with Tempe bright to the right of it toward the terminator. The terminator in question was the sunrise one, and we are offered 2 suppositions in explanation of the phenomenon. Either the white was due to a morning deposition of hoarfrost, which dissipated as the sun got up, or obliquity rendered some superficial deposit visible, which more vertical vision hid. That the former inference is the more probable seems hinted at by the simultaneous appearance from the 19th to the 26th of the other areas of white between the Mare and the pole. May the 26th was 88 days after the northern summer solstice and corresponded to July the 31st on the earth. Annals, Volume 3, Section 564. In this connection, mention may pertinently be made of Schiaparelli's repeated observation of regions that whiten with obliquity, a proclivity to which he particularly noticed Hellas and certain islands in the Mare Erythraeum to be prone. Here, as with the Mare Acidalium, we certainly seem to be envisaging cases of matutinal frost melted by midday under the sun's rays. End of Section 8. Reading by Florence.
Section 9 of Mars and its Canals by Percival Lowell. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information and to volunteer, please visit LibriVox.org. Recorded by Philip Aldred in Nottingham, UK. Mars and its Canals by Percival Lowell. Chapter 8, Climate and Weather. In gazing at the successive phases presented by the polar caps, as their annual history unrolls itself to view, beginning with vast white cloaks that in winter hide so effectively the planet's shoulders, to little round knobs that in summer sit like guardsmen's caps more or less askew upon the poles, the bodily eye sees only the glisten of far-off snow. The mind's eye, however, perceives something more, the conviction they carry of the presence of an atmosphere surrounding the planet. Elusive as water vapour is to sight for its transparency, and to spectroscopic determination for its earthly omnipresence, recognition of its existence elsewhere by deduction raises such reasoning at once to a more conspicuous plane than it might otherwise assume. Especially is this true when the deduction is itself conclusive, as is here the case. For it depends on a phenomenon not its own, but which are in their turn dependent on it. We are not even beholden to any knowledge of the substance composing the caps for the fundamental inference that an atmosphere surrounds them. Whatever that substance were, the fact that the caps dissipate and reform shows us with absolute certainty that they pass into the gaseous state, to be later solidified afresh. This gas consists of itself an atmosphere, while another phenomenon, to wit, their blue girdles as they melt, affirming their substance to be snow and ice, enables us to précis the fact that this gas is water vapour. From such premise given us by the polar caps, we are able to infer much more, by the help of the kinetic theory of gases. But the speed of parting by a planet with its gases is conditioned by the mean speed of each gas. Water vapour will therefore go before nitrogen, oxygen, or carbonic acid gas. If then we find it present over the surface of a planet, we are assured of the possibility that the other three may be there too, and from the similarity of matter in space, strong reasons to suspect that they actually are. Corroborative evidence of the accuracy of the deduction as to the presence of a Martian air is shown in several other ways. In the existence of clouds, to begin with. Rare as they are, these certainly float at times over parts of the planet, although it is doubtful whether they can be seen. Fortunately for assurance, we have other ways of ascertaining their presence than that of obscuration. Nor is it of account to the argument that they should be few and far between, as they unquestionably are. One single instance of such mediumistic support is enough to support the theory of a medium, and that instance has been more than once observed. Direct evidence of atmosphere is further forthcoming in the limb light. This phenomenon might be described as a brilliant obscuration. It is a circlet of illumination that swamps the features as they near the full edge of the disk, the limb of the planet, as it is called. Obliteration of the sort is evident more or less markedly at all times, and is not due to foreshortening as the broadest areas are affected. The fading out of the detail at the limb suggests nothing so much as a veil drawn between us and it, lighter in tint than what it covers. Such a veil can be none other than air, or the haze and cloud that air supports. From its effect, impartial in place and partial in character, cloud is inadmissible as a cause, and we are left with air charged with dust or vapour in explanation. Obscuration due to it should prove most dense at the limb, since there the eye has to penetrate a greater depth of it, just as on the earth our own air gives azure dimness to the distance, in deepened tinting as the mountains lie remote. Another bit of evidence lies in the apparent detection of a twilight arc. In 1894, measures made of the polar and equatorial diameters of the planet showed certain systematic residuals, left after all known corrections had been applied. The only thing which would account for them was the supposition that a twilight arc had been unconsciously seen and as unconsciously measured. In delicate quantities of the sort, too, great reliance cannot be put, but if the residuals be not referable to other cause, they give us not only further evidence of an atmosphere, but at the same time our only hint of that atmosphere's extent. From them it would seem that the air must be rare, not more than about 4 inches of barometric pressure as we reckon it, and probably less. A thin, high air, more rarefied than prevails upon our highest mountain tops. Corroborative of this is the aspect of the planet. From the general look of the disk, a scant covering of air is inferable. For one of the striking things about the planet's features is their patent exposure to our sight. Except in the winter time of its hemisphere, or in the spring after the greatest melting of the polar cap, nothing seems to stand in our way of an uninterrupted view of the surface, whether in the Arctic, temperate, or tropical zones. From the openness of its expression, however, too much case should not be made as we really know but little of how an atmosphere-enshrouded planet would look. We find no difficulty in seeing objects 100 miles away across the surface of the earth, and yet the thickness of the air strata in such horizontal traversing is manifold what it is when we look directly up. It is also out of all proportion laden with smoke. In the purer regions of the earth, a clear air imposes but little bar to sight, and conjures dust up far things startlingly distinct. Nevertheless, every evidence points to a thin air upon Mars. A priori reasoning, indirect deduction, and direct sight. Now from the thinness of atmosphere it would follow, other things equal, that the climate was cold. About this there has been much question, but less of answering reply. From the distance of the planet from the sun, it is certain less heat is received by it than falls upon the earth, in something like a ratio of 1 to 2, but that the amount effective is as the amount received is far from sure. The available heat is much affected by the manner of its reception. A blanket of air acts like the glass of a conservatory, letting the light rays in, but hindering the heat rays out. The light rays falling on the ground or the air are transformed into heat rays that, finding the return journey less easy, are consequently trapped. All substances are thus calorifiers, but water vapour is many times more potent than ordinary air to heat ensnaring. A humid air has a hothouse tangle to it, most perceptible. Now, what the relative percentage of water vapour in the Martian atmosphere may be, we do not know. The thinness of the Martian air has caused it to be likened to that upon our highest mountain peaks, which are in large part covered with perpetual snow. But the comparison is not well founded. A peak differs materially from a plateau in the countenance it gives to the heat falling upon it. On a plateau, each warmed acre of ground helps the retention of heat by its neighbour, while in addition to being destitute of side support, the higher winds generated about an isolated peak blow its own caloric away. Still less does any analogy hold between the two when the plateau is a world-wide one. From these considerations, it is evident glosses are possible upon the bald idea of a much lower temperature prevailing on the Martian surface than on the Earth's. Doubtless the theoretic cold has been greatly overdone. Reversely, recent observations tend to lower the apparent temperature disclosed by the features of the disk, and between the rising of the theoretic and the falling of the observed, we are left with a very reasonable compromise and reconcilement as a result. The various look and behaviour of the surface of Mars point to a mean temperature colder than that of the Earth, but above the freezing point of water, for reasons at least outside of the polar caps and during all but the winter months. Except at certain special spots, and possibly even there, frost is unknown at all times within the tropics, and except in winter in temperate latitudes. These anomalous localities, mentioned in the preceding chapter, may be said to be the exception that proves the rule of general non-glaciation. For if they be snow, they stand witness to its absence elsewhere upon the disk, and if they are not, they testify the more emphatically to the same effect. As between different parts of the surface, the tilt of the Martian axis and the greater length of the Martian seasons, the one the same as and the other the double of our own, tend to an accentuation of the heat in the temperate and Arctic or Antarctic zones. The greatest insolation on Earth is not, as we might suppose, at the equator, but at the parallels of 43.5 degrees north and south. Even the poles themselves receiving a quarter as much heat again on Midsummer's Day as ever falls to the lot of the line. This broad physical fact is equally true of Mars. While in the matter of consecutive exposure, Mars in summer outdoes the Earth, for the longer the seasons, the more nearly does the effective heat approach the received amount. Thus, both on the score of heat received and of the heat husbanded, these zones must be relatively warm, and this shows itself in the look of the surface. In summer it is clearly warmer within the polar regions than is the case on Earth, to judge by the effect. In winter the cold is doubtless proportionately severe. For the diurnal range of temperature we have less data. There is evidence pointing to chilly nights, but it is meagre, and we are left to fall back on the cold of our deserts at night for analogic condition of the state of things over the Martian desert levels after the sun goes down. If we are uncertain of the precise character of the Martian climate, we know on the other hand a good deal about the Martian weather. A pleasing absence of it over much of the planet distinguishes Martian conditions from our own. That we can scan the surface as we do, without practical interruption, day in and day out, proves the weather over it to be permanently fair. In fact, a clear sky, except in winter in many places even then, is not only the rule, but the rule almost without exceptions. In the early days of Martian study, cases of obscuration were recorded from time to time by observers, in which portions of the disk were changed or hidden as if clouds were veiling them from view. More modern observations fail to support this deduction, partly by absence of instances, partly by other explanations of the facts. Certainly the recorded one possible example has presented itself to me during the course of my observations, extending more or less over 11 years. Even in this case there was no obliteration, though a certain whiteness overspread an area near the equator temporarily. Position seemed to point to its identity with a cloud, which made its appearance about that time upon the terminator and lasted for some 36 hours. The cloud, however, showed evidence of being not the kind with which we are familiar, but a dust storm, in keeping, indeed, with the desert region, Chryse, in which it originated. With the exception of sporadic disturbance of the sort, the whole surface of the planet, outside the immediate vicinity of the polar caps, seems free from cloud or mist, and to lie perpetually unveiled to space. In the neighbourhood of the caps, however, and especially round about their edge, a very distinct pearly appearance is presented during the months at which the cap is at its maximum, or in other words, in the depth of its winter. Of a dull white hue and indefinite contour, the phenomenon suggests a cloud. Where it lies spread, no markings are visible, an absence explicable by obscuration due to interposed medium, but equally well by seasonal non-existence of the markings themselves, which from the general behaviour of these markings we know to be to some extent certainly the fact. Of the regions where the effect is noticeable, Hellas is the most striking. So conspicuously white during the winter of the southern hemisphere as to have been often mistaken for the polar cap, Its ghost shows thus almost regularly every Martian year. What is as suggestive as it is striking, the balance is confined to the solid circle constituting Hellas, and does not extend into the dark regions by which it is circumscribed. Hellas is as self-contained when it is powdered as when in its normal ochre or abnormal red it stretches like a broad buckler across the body of the disk. That the land there lies at a higher level than its surroundings is pretty certain, but that the difference can amount to enough to explain its silveriness as ice is improbable. In latitude, Hellas is distinctly temperate, lying between the parallels of 55 and 30 degrees. But on Mars this is no warrant of a like climate. Again, though close on the south to what constitutes the polar cap, it does not strictly form part of that cap, but occupies both in position and in kind a something intermediary between the frost-bound regions of periodic snow and the warmer ones of perpetual sunshine. It seems to be afflicted with the winter weather of the north of Europe, and to owe its pearly look at such times to the same cloud canopy that then distressingly covers those inclement lands. Similar in behaviour to it is the long chain of so-called islands that, beginning southwest of Thaumasia, runs thence westwards even to the eastern edge of Hellas. These belt the planet in a northwesterly direction by a strip of territory from 10 to 15 degrees wide, the medial line of which begins at 55 degrees south and ends in about 40 degrees. They are parted from the main bright areas by blue-green seas of about the same width as themselves, the Mare Cyrenum, the Mare Cimmerium, and Mare Tyrrhenum. Since the seas are not seas, the cause which might bound the snow, were they such, cannot be the cause here. Nevertheless, they have an effect of some sort on the isothermal lines, as is shown not only by latitude comparison with the state of things in Hellas, but with that in Thaumasia as well. For 30 degrees south is also the limit, apparently, of the white Thaumasia, where ochre deserts stretch 10 degrees further south still, the region in its southern part being white-mantled, in its northern part not. Here again, then, the ochre areas make exception to what affects the blue-green ones. Clearly, the blue-green regions temper the action of what gives them wintry cloak, but why they should do this is not easy to explain, on any supposition terrestrial or maritime. Bodies of water tend to foster the formation of clouds. So less markedly do areas of vegetation. Neither the old ideas then nor the new lend themselves in explanation. It may be that while here we seem to be envisaging cloud, we are in reality looking at hoarfrost. On the other hand, light cloud would show less, superposed over a dark background, than over an ochre one, and this, the simplest of all explanations, may be the true one. It is facts like these that intrigue us in the study of the Martian surface, by revealing conditions which render off-hand analogy with the earth unsafe. Indeed, we are more sure of some things which appear too strange to be true than of others so simple on their face as to enlist disbelief. Among the most difficult and perplexing are meteorological problems like the above. Here we can only say provisionally that while cloud best answers to the appearance, frost best fits the cause. For vegetation might melt frost, yet not dissipate cloud. By raising our conception of the mean temperature, the facts can, however, be reconciled, and this is probably the solution of the difficulty after all. As we saw in the annual history of the polar caps, a dimness somewhat different affects the northern cap in May and June. After the melting of the cap is well under way, a haziness sets in along its edge, which befuddles its outline and effectively hides what is going on within it. When at last the screen clears away, the cap is found to be reduced to its least dimensions. Such obstructing sheet looks to be more of the nature of mist, caused by the excessive melting of the cap. Unfortunately, there are here no patches of blue-green to test a possible partiality in its behaviour over such tracts, nor has similar action ever yet been remarked in the case of a cap of the southern hemisphere. Regular recurrence at the appropriate season of the planet's year, together with extensive action at the time, takes this springtide mist to some extent out of the dominion of weather into that of climate, for it prevails all round the cap, and repeats itself in places as each fresh spring comes on. At least it has done for the past 3 oppositions, at which it has been possible to observe well the Arctic zones. It is thus both general in its application and fixed in its behaviour. Nevertheless, it betrays something of the fickleness which characterises that most inconstant thing, weather. For it comes and goes, one thinks for good, only to find it there again some days later. Not less captious is the meteorologic action shown in the making of the new polar cap. When the northern one starts to form, vast areas of frost are deposited in a single night. These, however, are not permanent. The ground thus covered is during the next few days again partially laid bare. Then a new fall occurs, hiding the surface a little more completely than before, and the lost domain is more than regained. By such wave-like advance and recession, the tide of frost creeps over and submerges the Arctic regions as the late summer passes into autumn. In this alternate coming and going with succeeding days, we have an unsteadfastness of action most fittingly paralleled by our own weather. It would seem that local causes, there as here, are superposed upon the orderly progress of the seasons, and though at the oncoming of the autumn the cold is steadily gathering strength, nevertheless warm days occur now and then to stay its hand, only to be succeeded in their turn by frosts more biting than before. Even on Mars, nothing in the way of weather is absolutely predicable, but its impredicability. End of section 9.
Section 10 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Mike Ferry 252. In all ways but one, our scrutiny of the planet is confined to such view as we might get of it from the car of a balloon poised above it in space, from which disadvantage point we should see the surface only as a map spread out below us, a matter of but 2 dimensions. The exception consists in the observation of what are called projections, irregularities visible when the disk is gibbous upon that edge of the planet where the light fades off. Striking phenomena in themselves, they are of particular value for what may be deduced from them, for by them we are afforded our only opportunity of gaining knowledge of the surface other than in plan, and thus of determining between peak, plateau, or plain, that to a bird's eye view alike lie flattened out to one dead level. It might at first be thought that our best chance of noting any elevations or depressions of the Martian surface lay in catching that surface in profile, by scanning the bright edge of it, which stands sharp cut against the sky and is called the limb. For this is practically what we do on Earth when we mark a mountain against the horizon and measure its height by triangulation. Unfortunately, the method fails in the case of Mars because of the great distance we are away. Unless the planet were distinctly more generously equipped than the Earth in the matter of mountains, nothing could be hoped from so forthright an envisaging. So relatively insignificant to the size of its globe is the relief of the Earth's surface that an orange skin would seem grossly rough by comparison. The same proves true for Mars. With the greatest magnification we can produce, the Martian limb still appears perfectly smooth. Luckily, while direct vision is thus impossible, oblique illumination enables us to get an insight into the character of the surface we had otherwise been denied. When mountains or valleys chance to lie upon the boundary of light and darkness, the rim of the disk, known as the terminator in contradistinction to the limb where the surface itself comes to an end, they make their presence evident through an indirect species of magnification. The elongate effect of oblique lighting, with the practical instance of it, everyone is familiar who has walked by night along a road imperfectly starred at intervals by electric lights, startled between posts by what seemed deep holes and high furrows. He has involuntarily imitated a spavined horse for fear of stubbing his toes, only to encounter, when his foot fell a surface on contact surprisingly smooth. The slant illumination, by lengthening the shadows, had painfully deceived him into exaggerated inference of irregularity. What proves disturbing to a wayfarer misguided by arc lights is made to do the eye's service when it comes to planetary interpretation. On the boundary of light and shade, those parts of the surface where it is sunrise or sunset upon the planet, the sun rays fall so athwartwise as to throw enormous shadows from quite small elevations to an eye so placed as to view the surface with anything approaching perpendicularity. A mountain mass there will thus proclaim itself by protracted profile upon the plain in hundredfold magnification. Similarly, a peak there will advertise its height by catching the coming or holding the lingering light at many times the distance of its own elevation from the night side of the planet. Here, if anywhere, then, could mountains be expected to disclose themselves, and here, when existent, they have, as a matter of fact, been found. Our own moon offers us the first and easiest example of such vicariously visible relief. When the moon is near the quarter, and for 3 or 4 days on either side of that, a keen eye can usually detect one or more knobs, like warts projecting from its terminator, easily distinguished from the limb, both by reason of being less bright and of being bounded by a semi-ellipse instead of a semicircle. If a telescope or even an opera glass be substituted for the eye, it is possible to see what causes them. The knob resolves itself into the illuminated rim of a crater separated from the main body of the visible moon by the seemingly black void of space. The peak has caught the sunlight, while its foot in the country between it and the illuminated surface still lies shrouded in shadow. For measurement of the distance, the sun-tipped peak seems to stand aloof from the line where the plane itself is touched by the light. The height of it above that plane may be calculated. In this way have been found the heights of the mountains of the moon. Incidentally, rain outstrips broad, for pinnacles no lunarian could scale, both for their precipitous inaccessibility and their loftiness. Man is measured without so much as setting foot upon their globe. At each lunar sunrise, and again at lunar sunset, these old crater walls show their crescent coronets tipped the reverse way, and peaks higher than the Himalayas make gigantic gnomons of themselves with hands outstretched to grasp the plains. In this manner, a lunar peak of 15,000 feet shows its presence to the unaided eye. With so much for starting point, we can calculate how low an elevation could similarly be made out on Mars under a like phase illumination. Now, in spheres of different diameters, the distance out from the terminator for a given height is as the square root of the diameter. Mars has about twice the size of the moon. In consequence, if we saw the planet at the same distance off as the moon, the height of a peak upon it sufficient to cast an equal shadow or be seen at an equal separation from the terminator need be but 2/3 as high. To see it thus equidistant, a power of 250 or 300 is necessary, dependent upon the opposition. Twice this power may at times be used, and by the same reasoning this would reduce the height sufficient to show by 4 or 2 something like 2,500 feet. This, then, will be the theoretic limit of the visible, a limit needing to be somewhat increased because of the imperfection of our air. Having found thus what should be visible on Mars, we turn now to see what it is. At once we find ourselves confronted with the very unlunar state of things. Common upon the face of the moon, excrescents of the terminator are rare on Mars. The first ever seen was detected by a visitor at the Lick Observatory in 1888. Since then, they have been repeatedly noticed both at the Lick and elsewhere. But although observers are now on the watch for them, they are not very frequently chronicled, not because of everyday occurrence. Much depends upon the opposition, some approaches of the planet proving more prolific of them than others. How rare they are, however, may be gathered from the fact that the last 3 oppositions have disclosed but 1 apiece. An account of the great projection of May 25th, 1903, will give an idea of the extent and interest of the phenomenon, and will serve to show to what cause we must attribute all such that have been visible on Mars. For the behavior of this one was typical of the class. About 8:30 in the evening of May 26th, 1903, Mr. V.M. Slipher, astronomer at Flagstaff, shortly after taking over the telescope then directed upon Mars, suddenly noticed a large projection about halfway up the terminator of the planet. He at once sent word of the fact, and the observatory staff turned out to see it, for a projection has for workers on Mars the like interest that a new comet possesses for astronomers generally. In this case, the phenomenon was specially potent in that it was the first to be detected that year. Its singularity was amply seconded by its size, for it was very large, its extent both in length and height being excessive. When I first saw it, the projection consisted of an oval patch of light, a little to the north of the center of the phase ellipse, lying parallel to the terminator, but parted from it by darkness to the extent of half the projection's own width. It made thus not simply an excrescence, but a detached isolate of light. It was easily seen by all those present, and was carefully studied from that time on by Mr. Slipher and me. Both of us made drawings of it alternately at intervals, as well as micrometer measures of its position. Next to its great size, the most striking feature about it was its color. This, instead of being white or whitish, was ochre-orange, a hue closely simulated to the tint of the subjacent parts of the disk, which was the region known as crisis. This distinctive complexion was kept throughout the period of its apparition. At the same time, Baltia, a region to the north of it, and synchronously visible close upon the terminator, showed whitish. The seeing was good enough to disclose the Phison on Euphrates double, the power, a magnification of 310, and the aperture, the full aperture of the 24-inch objective. From the time it was first seen, the detached patch of light crept in toward the disk, the illuminated body of the planet. 4 minutes after I noted it, the dark space separating it from the nearest point of the terminator had sensibly lessened. So it continued with some fluctuations intrinsic to the atmospheric difficulties of observations generally and to the smallness of the object itself, to become gradually less and less salient. It lasted for about 40 minutes from the moment it had first appeared to Mr. Slipher, and then passed from sight to leave the edge of the planet, smooth and commonplace again. The measures made on it show that it lay, when first seen, in longitude 39.7 degrees, latitude 18.5 degrees north, and that its highest point stood 17 miles above the surface of the planet. It was 300 miles long. These are my own figures, from which Mr. Slipher's do not substantially differ. The return of the part of the planet where it had been seen was eagerly awaited the night after by both observers to see if it would bring the projection with it. For only once a day is the same region of Mars similarly presented. But in order not to miss the projection should it be ahead of time, observations were begun before it was due. Shortly after they were started, there appeared higher up the terminator, and therefore farther north than had been the case the night before, a small projection. It was with difficulty made out and its position measured. Without careful watching, it must have been missed altogether. As it was, it differed, in every respect, from that of the preceding day. It was not nearly so high, not nearly so large, and lay in a different place on the planet, being now in longitude 31.7 degrees, latitude 25.5 degrees. Either the two, therefore, were totally different things, or the projection had moved, in the elapsed interval of time, over 7 degrees of latitude and 8 degrees of longitude, a distance of 390 miles in 24 hours, where the previous projection had been nothing shown. On the following night, May 28th, no trace of anything unusual could be seen anywhere. We are now concerned to inquire to what this series of appearances could have been due. The first observers of projections on Mars had unhesitatingly attributed them to the same cause that produces projections on the moon, to wit, mountains. Such they were held to be in France and at the Lick. This view, however, was in 1892 disputed by W. H. Pickering, who considered them to be not mountains but cloud, and this view was strongly supported by A. E. Douglas, and a discussion of a large number of them observed in 1894 at Flagstaff. The mountain theory of their generation was finally shown to be untenable, and their ascription to cloud conclusively proved to be the correct solution by the observations of a remarkable one made in December 1900 and the careful study to which by the writer they were subjected. We shall now explain how this was done, and we will begin by pointing out that the fact that only a single specimen of the phenomenon was visible at each of the three oppositions of 1900, 1903, and 1905 was itself conclusive, rightly viewed, of their non-mountainous character. This conclusion follows at once from the isolatedness of the phenomenon, for a mountain cannot change its place. Now the shift in the aspect presented by the planet's disk from one night to the next is not sufficient to alter perceptibly the appearance shown by anything upon its edge on the two occasions. If then a peak stood out upon it one evening, the peak should again show salient when the region reached the same position upon the succeeding night, that nothing then was seen where something had previously been visible proved the phenomenon, not that of a mountain peak, since what produced the projection was clearly not fixed in place and therefore not attached to the soil. Now the only other thing capable of catching the light before it reached the surface would be something suspended in the air, that is, a cloud. Deduction, therefore, from the rarity of the phenomenon alone showed that the projections must be clouds. Their behavior in detail entirely corroborates this deduction from their intermittence. Such was shown by the action of the projection of December 6, 1900, as set forth in a paper before the American Philosophical Society, and such again by that of the one of May 26, 1903, as we shall now note. To begin with, we notice that the projection seen on May 26 was not found either in situ or in size on May 27th, and had wholly vanished on May 28th, though the seeing was substantially the same, if not better, on the 2 nights succeeding that of its original detection. Hence, in its own instance, this projection proved an alibi irreconcilable with the character of a mountain mouse, but it did more. It not only was not on the second evening what and where it had been on the first, but the remains of it visible on the second occasion showed clearly it had moved in the meantime. Furthermore, it was disappointing as it went, for it was very much smaller after the lapse of 24 hours. The something that caused it was not only not attached to the soil, but was moving and dissipating as it moved. Only one class of bodies known to us can account for these metamorphoses, and that is cloud. But what kind of cloud are we to conceive it to be? Our ordinary vapor clouds are whitish, and this would be still more their color could they be looked at from above. The Martian cloud was not white, but tawny, of the tint exhibited by a cloud of dust, nor could this color have very well been lent by its sunrise position, for other places equally situated to be tinged by the hues of that time of day, Baltia to wit, showed distinctly white, so that we must suppose it to be what it looked, a something of the soil, not beholden to atmospheric tinting for its hue. A vast dust cloud traveling slowly over the desert and settling slowly again to the ground. Precisely the same general course of drifting disappearance was taken by the projection of December 7th and 8th, 1900, and this too stood a unique apparition in the annals of its opposition. Clouds then, and not mountains, are the explanations of the projections on Mars, differing thus completely from the lunar ones. End of section 10 of Mars and Its Canals by Percival Lowell, recorded by Mike Ferry 252.
Section 11 of Mars and Its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Anita Slama Martinez. Mars and Its Canals by Percival Lowell. Chapter 10. The Blue-Green Areas. Descending now equatorwards from the polar regions, and there in part paleocrystic, in part periodic coating of ice, we come out upon the general uncovered expanse of the planet, which in winter comprises relatively less surface than on Earth, but in summer relatively more. 40 degrees and 86 degrees may be taken as the mean hymeal and estival limits, respectively, of the snow on Mars, 45 and 75 as those of the Earth. Whatever ground is thus spared of superficial covering on Mars lies fully exposed to view, thanks to the absence of obscuring cloud, and it is at once evident that the terrain is diversified, patches of blue-green alternating with stretches of reddish ochre. Of the two opaline tints, the reddish ochre predominates, fully 5/8 of the disk being occupied by it. It was early evident in the study of the surface of Mars that its ochreish disk was not spotless. Huygens, in 1659, saw the Syrtis Major. From this first fruit of areography dates, indeed, the initial recognition of the planet's rotation, for on noting that the marking changed its place, he inferred a turning of the planet upon itself in about 24 hours. 13 years later, he observed and drew it again, and this time in company with the polar cap. Again, after 11 more years, he depicted it for the third time, and now so changed because of the different tilt of the planet toward the earth that it may be doubted whether Huygens himself recognized it for the same, but that he drew it correctly a globe of Mars will at once show. From such small beginning did areography progress to the perception of permanent patches of a somber hue distributed more or less irregularly over the disk. Impressing the observer simply as dark at first, they later came to be recognized as possessing color, a blue-green, which contrasted beautifully with the reddish ochre of the rest of the surface. Cassini, Maraldi, Bianchini, Herschel, Schroter all saw markings which they reproduced. Finally, with Beer and Medler came the first attempt at a complete geography. In and out through the ochre was traced the blue, commonly in long Mediterraneans of shade, but here and there in isolated Caspians of color. With our modern telescopic means, the dark patches are easily visible, the very smallest glass sufficing to disclose them. When thus shown, they much resemble in contour the dark patches on the face of the moon as seen with the naked eye. Now these patches were early taken for lunar seas and received names in keeping with the conception, as the Sea of Serenity, the Sea of Vapors, and so forth. Following the recognition of a like appearance, like appellatives were given to the Martian markings, and the Mare Serenum, or Sea of the Sirens, the Mare Cimmerium, and others sufficiently proclaim what was thought of them at the time they were thus baptized. Indeed, if a general similarity be any warrant for a generic name, they were not at the time ill-termed. For common to all three bodies, the earth, the moon, and the planet Mars, is the figuration of their surfaces into light areas and dark. In the Martian disk, as in the lunar one, we seem to be looking at a cartographic presentation of some strange geography suspended in the sky, the first generic difference between the two being that the chart is done in chiaroscuro for the moon, in color for Mars. On mundane maps, we know the dusky washes for oceans, so on the moon it was only natural to consider their counterparts as Maria, and on Mars as seas, nor did the blue-green hue of the Martian ones detract from the resemblance. But in something other than color these markings are alike. In fact, color could hardly be excuse for considering the lunar Maria what their name implies, for distinctive tint is lacking in them, even to the naked eye. It was in form that the likeness lay. Their figures were such as our own oceans show, and allowing for a sisterly contrast amid a sisterly resemblance, the lunar Maria or the Martian seas might well have been a similar origin to those with which our schoolboy's study of atlases had made us familiar. Thus did similarity in look suggest similarity in origin, and intuitive recognition clothe its objects with the same specific name. Considerable assumption, however, underlay the pleasing simplicity of the correlation on other grounds, consequent not so much upon any lack of astronomic knowledge as, curiously, upon a dearth of knowledge of ourselves. We know how other bodies look to us, but we ignore how we look to them. It is not so easy to see ourselves as others see us, for a far view may differ from a near one, and a matter of inclination greatly alter the result. Owing both to distance and to tilt, we lack that practical acquaintance with the aspect of our own oceans viewed from above, necessary to definite predication of their appearance across interplanetary space. Our usual idea is that seas show dark, but it is also quite evident that under some circumstances they appear the contrary. It all depends upon the position of the observer and upon the position of the sun. Their usual ultramarine may become even as molten brass from indirect reflection, while on direct mirroring they give back the sun with such scarce perceptible purloining of splendor as to present a dazzling sheen not to be gazed upon without regret. Canopied by a welkin, they assume its leaden hue, while at the same time their shores, less impressionable to borrowed lighting, show several tints darker than themselves. Surfaces so sensitive to illumination hardly admit of more accusable tint than a chameleon. Nevertheless, we are probably justified in our conviction that, perpendicularly visaged, they would on the whole outdo in sombreness land round about them, and so be evident as dusky patches against brighter ground. One phenomenon we might with some confidence look to see exhibited by them were the oceans, and that is the reflected image of the sun visible as a burnished glare at a calculable point. Specular reflection of the sort was early suggested in the case of Mars, and physical ephemerides for the planet registered for many years the precise spot where the star-like image should be sought, but it was never seen. Yet not till the marine character of the Martian seas had been otherwise disproved was the futile quest for it abandoned. Indeed, it was a tacit recognition that our knowledge had advanced when this column in the ephemeris was allowed to lapse. On this general marine ascription doubt was first cast in the case of the moon. So soon as the telescope came to be pointed at our satellite, it was evident that the darker washes were not water surfaces at all, but very palpably plains. Long, low ridges of elevation stood out upon them like prairie swells, which grew in visible relief according to the slanting character of the illumination. Cracks or rills, too, appeared near their edges, and craters showed in their very midst. Patently solid, they betrayed their constitution not only by diverse topography, but by diversified tint. All manner of shades of neutral tone mottled their surface, from seeming porphyry to chalk. Belief perforce departed when the telescope thus pricked the bubble, evaporating as the water itself had done long before. So much was known before the Mars markings were named. Nevertheless, humanity, true to its instincts, promptly proceeded to commit again the same mistake, and cheerfully undeterred by the exposure of its errors in the case of the moon, repeated the christening in the case of Mars. So sure was it of its ground that what it saw was not ground, that though the particular appellatives of the several seas were constantly altered, rebaptisms, while changing the personal, kept the generic name. Dawes Ocean, for example, later became l'Oceanuten, and later still the Mare Erythraeum, but remained set down as much a sea as before. About 13 years ago, however, what had befallen the seas of the moon befell those of Mars, the loss of their character. It was first recognized through a similar exposure, but the fact was led up to and might have been realized in consequence of quite a different line of evidence. The initial thing to cast doubt upon the seas being what they seemed to be was the detection of change in their aspect. That the detection was not made much earlier than actually happened shows how a phenomenon may elude observation if scrutiny be not persistent, and its results from time to time not carefully compared. Schiaparelli was the one who first noticed variation in the look of the seas, and the discovery was as much due to the assiduity with which he followed the planet opposition after opposition as to the keenness with which he scanned it. The noting of change in the blue-green areas constituted, in fact, one of the first fruits of systematic study of the planet. Change in configuration, that is, alteration of area, preceded in recognition alteration of tint. Thus the Syrtis Major showed larger to him in 1879 than it had in 1877. This was natural, difference of degree being a more delicate matter to perceive than its effect upon extent. From change of area, his perception went on to change of tone. In his own words, what he noticed was this: Memoria 6, 1888. No less certain is it that from one opposition to another one notices in the seas very remarkable alterations of tone. Thus the regions called Mare Cimerium, Mare Serenum, and Solis Lacus, which during the years 1877 to 1879 could be numbered among the most somber on the planet, during the succeeding oppositions became less and less black, and in 1888 were of a light gray, hardly sufficient to render them visible in the oblique opposition in which all three found themselves. On the other hand, at the very same moment, the Mare Acidalium and the Lacus Hyperboreus showed very dark. The latter indeed appeared nearly black, although seen as tilted as the Syrtis and the equatorial bays. The condition of the regions called seas is therefore not constant. So much is unquestionable. Perhaps the change produced in them has to do with the season of the planet's year. Holding as he did the then prevailing view that the blue-green regions were bodies of water, he regarded those of intermediate tint as vast marshes or swamps, and he accounted for change of hue in them as due to inundations and occasions of drying up. In consequence of losing their water, the seas, he thought, had in places become so shallow that the bottom showed through. Plausible on the surface, this theory breaks down so soon as it is subjected to quantitative criticism. For the moment we try to track the water, we detect the inadequacy of the clue. The enormous areas over which the phenomenon occurs necessitates the establishing an alibi for all the lost water that has gone. Drying up on such a scale would mean the removal of many feet of liquid over hundreds of thousands of miles in extent. To produce any such change in appearance as we witness, even on the supposition that these seas were none too deep to start with, would involve lowering the level of the water by from 5 to 20 feet throughout 2/3 of the whole surface of the southern hemisphere. This would leave a heap of waters to be accounted for, bewildering in its immensity. The myriad tons of it must be disposed of, either by drainage into other regions, or by being caught up into the sky. In this emergency, it might seem at first as if the polar cap of the opposite hemisphere offered itself as a possible reservoir for the momentarily superfluous fluid. But such hoped-for outlet to the problem is at once closed by the simple fact that when the lightening of the dark regions of the southern hemisphere takes place, the opposite polar cap has already attained its maximum, in fact, has already begun to melt. It therefore absolutely refuses to lend itself to any such service. This was not known to Schiaparelli's time, the observations which have established it, by recording more completely the history of the cap, having since been made. Indeed, it was not known even at the time when the writer, in 1894, showed the impossibility of the transfer on other grounds, to wit, on the fact of no commensurate concomitant darkening of the surface elsewhere, and on the manifest non-complicity, if not impotency, of the Martian atmosphere in the process. The transference of the water to other dark patches in the northern hemisphere fails of sufficiency of explanation because of the limited extent of such areas on that side of the globe, while the air is quite as incapable of carrying away any such body of liquid, though the whole of it were at the saturation point, not to mention that there exists no sign of the attempt. The reader will find this reasoning set forth in Mars, published 11 years ago. He will now note, from what has been said above about the northern polar cap, that continued observations since have resulted in opening up another line of proof, which has only strengthened the conclusion there reached. The coup de grace, however, to the old belief was given when the surface of the dark areas was found to be traversed by permanent lines by Pickering and Douglas. Continued observation showed these lines to be unchangeable in place. Now permanent lines cannot exist on bodies of water, and in consequence the idea that what we looked on there were water surfaces had to be abandoned. Thus we now know that the markings on both the Moon and Mars, which have been called Maria, are not in reality seas. Yet we shall do well still to keep the old-fashioned sonorous names, Mare Erythraeum, Mare Serenum, and their fellows, because it is inconvenient to change, while, if we please, we may see in their consecrated Latin couching the fit embalming in a dead language of a conception that itself is dead. End of section 11.
Section 12 of Mars and its Canals. This is a LibraryVox recording. All LibraryVox recordings are in the public domain. For more information or to volunteer, please visit libraryvox.org. Read by Andrew Connolly. Mars and its Canals by Percival Lowell. Chapter 11. Vegetation. Since closer acquaintance takes from the Maria their character of the seas, we are led to inquire again to their constitution. Now, when we set ourselves to consider to what such appearances could be due, we note something besides sea, which forms a large part of our Earth's surface, and would have very much what we suppose the latter's aspect from afar to be, not only in tone, but in tint. This something is vegetation. Seen from a height and mellowed by atmospheric distance, great forests lose their green to become themselves ultramarine. To dispossess a previous conception is difficult, but so soon as we have put the idea of seas out of our heads, a vegetal explanation proves to satisfy the phenomena, even at a first glance, better than water surfaces. In their color, blue-green, the dark areas exactly typify the distant look of our own forests, whereas we are not at all sure that seas would. From color alone, we are more justified in deeming them vegetal than marine. But the moment we go further into the matter, the more certain we become of being upon the right road. With increased detection, the markings they reveal and the metamorphosis they undergo, while pointing away from water, point as directly to vegetation. All the inexplicabilities which the supposition of water involves find instant solution on the theory of vegetal growth. The non-balancing of the areas of shading and their shift from one part of the disk to another no longer becomes a circumstance impossible to explain, but a necessary consequence of their newfound character, denoting the time necessary for vegetation to sprout. The change of hue of vast areas from blue-green to ochre no longer presupposes the bodily transference of the thousands of tons of substances, but the quiet turning of the leaf under the autumnal frosts. Even the fact that they occupy those regions most fitted by figure to contain oceans fits in with the same conception. For that the Martian equivalents of forests and moorland, trees and grass, should grow now in the lowest parts of the planet's surface, is what might not unreasonably be expected from the very fact of their being low, since what remained of the water would tend both on the surface and in the air to drain into them. For the change in question to be vegetal, it must occur at the proper season of the planet's year. This we must now consider. We have said that Schiaparelli detected change in the blue-green regions and suspected this change of seasonal affiliation. He inferred this from piecing together the aspects of different seasons of different years as shown in consecutive Martian oppositions. To mark it actually take place in a single Martian year came later. In 1894, at Flagstaff, the southern hemisphere was presented during its late spring and early summer. It was observed, too, for many of our months in succession. During this time, the planet was specially well circumstanced for study of the change in that hemisphere, both by reason of the appositeness of the season and of the unusual size of the disk. Advantage was taken of the double event to a recording of the consecutive appearances certain regions underwent, and the contrasted states thus exhibited were such as to clearly betoken the action of seasonal change. What Schiaparelli had thus ably inferred from diverse portions of different Martian years was in this case shown occurring in one and the same semestral cycle. Usually the change of hue seems essentially one of tone. The blue-green fades out, getting less and less pronounced, until in extreme cases only ochre is left behind. It acts as if the darker color were superimposed upon the lighter and could be, to a greater or lesser extent, removed. This is what Schiaparelli noted and what was seen in 1894 at Flagstaff. 3 views en suite of the chain of changes then observed are shown in Mars, the region known as Hesperia being central in each. Comparison of the 3 discloses a remarkable metamorphosis in that promontory, a rise into visibility by a paling of its complexion. Nor is the contrast confined to it. Changes as salient will be noticed in the pictures over the other parts of the disk. There have been instances, however, of a metamorphosis so much more strange as to deserve exposition in detail. One where not tone simply is involved, but where a quite new tint has surprisingly appeared. On April 19th, 1903, when, after being hidden for 30 days, owing to the different rotation periods of the two planets, the Mare Erythraeum, the largest blue-green region of the disk, and laying in the southern hemisphere, rounded again into view, a startling transformation stood revealed in it. Instead of showing blue-green as usual, and as it had done 6 weeks before, it was now of a distinct chocolate brown. It had been well seen at its previous presentation, so that no doubt existed of its then tint. At that time, the Martian season corresponded to December 30 in our calendar. 18 Martian days had since elapsed, and it was now January 16 there. Metamorphosis had taken place, therefore, shortly after the winter solstice of that part of the planet. The color change that had supervened proved permanent. For the next night, the region showed the same brown hue, and so it continued to appear throughout the days that it was visible. 2 months passed, and then the chocolate hue had vanished, gone as it had come, and the Mare had resumed its usual tint, except for being somewhat pale at the south. It had come to be February 21st on Mars. Timed and tabulated, the metamorphosis through which the Mare passes stands out thus. Mare Erythraeum, 1903. Mundane date, February 16. After summer solstice, before equals minus, after equals plus, minus 10. Martian date, December 16. Aspect, blue-green. Mundane date, March 20. After summer solstice, plus 22. Martian date, January 1. Aspect, blue-green. Mundane date, April 19th. After summer solstice, plus 52. Martian date, January 16th. Aspect, chocolate. Mundane date, April 22nd. After summer solstice, plus 55. Martian date, January 18. Aspect, chocolate. Mundane date, May 26. After summer solstice, plus 89. Martian date, February 4. Aspect, faint chocolate. Mundane date, May 30. After summer solstice, plus 123. Martian date, February 22. Aspect, faint blue-green. Mundane date, July 7. After summer solstice, plus 130. Martian date, February 25. Aspect, faint blue-green. The culmination of the transformation seems to have taken place about 60 days after the southern winter solstice, or in the depths of the Martian winter of that hemisphere. This is certainly just the time at which vegetation should be at its deadest. The northern and southern portions of the Mare did not behave alike in taking on the chocolate tint. From the notes made about them during the opposition, it appears that the latter was later than the former in undergoing the metamorphosis, as will be seen from the following depth of the blue-green estimated in percentages shown at different dates, calling the deepest tone ever exhibited by it unity. Martian date, December 16, northern, 50%, southern, 50%. Martian date, January 1, northern, 50%, southern, 50%. Martian date, January 17, northern, 0%, southern, 0%. Martian date, February 5, northern, 25%, southern, 0%. Martian date, February 24, northern, 50%, southern, 25%. From this table, we may place the lowest point of the blue-green tint as reached about the 22nd day of January for the northern and the 5th of February for the southern part. This would indicate that the wave of returning growth came from the north, not the south, an important fact as we shall see later in studying the actions of the canals. At the next opposition in 1905, a reoccurrence of the transformation was watched for, and not in vain. It occurred, however, somewhat later in the Martian season. On December 27 of the planet's current year, the Mare Erythraeum was still as usual, blue-green, nothing out of the ordinary being remarked in it, and so it was on its January 17, although the southern edge was darker than the northern. It looked certainly as if the metamorphosis were this year to be omitted, but such was not the case. When the region again came round on February 1 of the Martian calendar, there the strange tint was as unmistakable as it had been on its original occurrence. Not only was the Mare Erythraeum so colored, but on February 5 Martian, the northern portion of the Mare Cimmerium was observed to be similarly affected. In the Mare Erythraeum, the anomalous chocolate hue was confined to a belt between the latitudes of 10 degrees and 20 degrees south of the equator. In the Mare Cimmerium, it stretched a little higher, from 10 degrees at the west to 25 degrees at the east. It is noteworthy that the southern portion of the latter showed blue at the time the northern showed brown. Then the metamorphosis proceeded as shown in the following table. Mare Erythraeum, 1905. Mundane date, January 25. Days after winter solstice of southern hemisphere. 12. Martian date, December 27. Aspect, blue-green. Mundane date, March 6. Days after winter solstice of southern hemisphere. 52. Martian date, January 16. Aspect, blue-green. Mundane date, April 4. Days after winter solstice of southern hemisphere. 81. Martian date, January 31. Aspect, chocolate. Mundane date, April 12. Days after winter solstice of southern hemisphere. 89. Martian date, February 4. Aspect, chocolate. Mundane date, April 30. Days after winter solstice of southern hemisphere. 107. Martian date, February 13. Aspect, faint chocolate. Mundane date, May 8th. Days after winter solstice of southern hemisphere. 115. Martian date, February 17. Aspect, faint chocolate. Mundane date, May 12th. Days after winter solstice of southern hemisphere. 119. Martian date, February 19. Aspect, faint blue-green. Mundane date, June 11. Days after winter solstice of southern hemisphere. 149. Martian date, March 6. Aspect, faint blue-green. Mundane date, June 15. Days after the winter solstice of the southern hemisphere. 153. Martian date, March 8. Aspect, faint blue-green. Mundane date, July 16. Days after the winter solstice of the southern hemisphere. 184. Martian date, March 23. Aspect, pale bluish-green. Here, as in 1903, a chromatic rise and fall is evident. The culmination of the change occurring in Martian early February, about 90 days after the winter solstice. That it was not of long duration is also indicated. If we examine the evidence for the two portions of the Mare separately, the northern and the southern, as in 1903, we find it as follows. Martian date, December 27. Northern, 50%. Southern, 50%. Martian date, January 16. Northern, 50%. Southern, 50%. Martian date, February 2. Northern, 0%. Southern, 20%. Martian date, February 16. Northern, 10%. Southern, 20%. Martian date, March 7. Northern, 25%. Southern, 25%. Martian date, March 23. Northern, 30%. Southern, 30%. Here, again, a slight retardation in the advent of the metamorphosis is observable in the southern portion. There would seem to be a difference in the time of the change between the 2 years of 15 days, 1905 being that much the later. But with points of reference themselves 30 days apart, it is possible the two more nearly coincide than here appears. Unlike the ochre of the light regions generally, which suggests desert pure and simple, the chocolate brown precisely mimicked the complexion of fallow ground. When we consider the vegetal-like, blue-green, that it replaced, and remember further the time of year at which it occurred upon both these Martian years, we can hardly resist the conclusion that it was something very like fallow field that was there uncovered to our view. For the reoccurrence of the phenomena on 2 successive years, it is likely that it annually takes place. That it is seasonal can scarcely be doubted from the timeliness of its occurrence, and that different portions of its terrain successively underwent their metamorphosis shows further that it followed a law peculiar to the planet, to which we shall be introduced when we come to consider the phenomena of the canals. Instances of relative hue in different dark patches, corroboratory of seasonal variation and therefore of vegetal constitution, might easily be adduced. Thus, in 1905, during the summer of the northern hemisphere, the Mare Acetylum was notably darker than the Mare Erythraeum, to the north of it, which is what the law of seasonal variation would require, since it was June in the one, December in the other at the time. But we need not to add example to example or proof to proof, for there are no phenomena that could contradict it. We conclude, therefore, that the blue-green areas of Mars are not seas, but areas of vegetation. Just as reasoning to a negative result drifts us to the first conclusion, so reasoning to a positive one lands us at the second. End of section 12.
Section 13 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Mars and its Canals by Percival Lowell. Chapter 12. Terraquaciousness and Terrestriality. With the vanishing of its seas, we get for the first time solid ground on which to build our Martian physiography. The change in venue from oceans to land has produced a complete alteration in our judgment of the present state of the planet. It destroys the analogy which was supposed to exist between Mars and our Earth, and by abolishing the actuality of oceans there, seems, metaphorically, to put us at first all the more at sea in our attempt to understand the planet. But looked at more carefully, it turns out to explain much that was obscure, and in so doing gives us at once a wider view of the history of planetary evolution. The trait concerned is cosmic. Study of the several planets of our solar system, notably the Earth, Moon, and Mars, reveals tolerably legibly an interesting phase of a planet's career, which apparently must happen to all such bodies, and evidently has happened or is happening to these three. The transition of its surface from a terraqueous to a purely terrestrial condition. The terraqueous state is well exhibited by our own Earth at the moment, where lands and oceans share the surface between them. The terrestrial is exemplified by both the Moon and Mars, on whose surfaces no bodies of water at present exist. That the one state passes by process of development into the other, I shall now give my reasons for believing. In the first place, the appearance of the dark markings both on the Moon and Mars hints that those seas no longer, they were seas once upon a time. On the Moon, not only does their shape suggest this previous condition, but the smooth and even look of their surface adds to the cogency of the inference. More important, however, than either of these characteristics, and confirmatory of both, is the fact that the great tracts in question seem to lie below the level of the corrugated surface, which is thickly strewn with volcanic cones. Their level and their levelness feign explanation into one another. The first makes possible the former presence of water, the second speaks of its effect, for their flat character hints that these areas were held down at the time when the other parts of the surface were being violently thrown up. That they can themselves be cooled lava flows, their extent and position seem enough to negative, to say nothing of the fact that they should in that case lie above, not below, the general level. Something, therefore, covered them during the Moon's eruptive youth and disappeared later. Such superincumbence may well have been water, under which the now great plains lay then as ocean bottoms. Deep-sea soundings in our own oceans betray an ocean floor of the same extensive sort, diversified as on the Moon. To call the lunar maria seas may not be so complete a misnomer after all, but only a resurrecting in epitaph what was the truth in its day, only doubtfully offered here for the Moon. For Mars the inference seems more sure. Here again the dark regions not only look as they should had they had an earlier history, but they too seem to lie below the level of the surface round about. When they pass over the terminator, they invariably show as flattenings upon it, as if a slice of the surface had been pared off. Such profile in such pass is what ground at a lower level would present. Undoubtedly a part of the seeming depression is due to relative absence of iridation, consequent upon a more sombre tint, but loss of light, hardly seems capable of the whole effect. In the case of Mars, then, as with the moon, a mistaken inference builded better than it knew, if indeed we should rightly consider an inference to be mistaken which on half data lands us at the right door. From the aspects of the dark regions we are led, then, to regard Mars as having passed through that stage of existence in which the earth finds itself at the moment, the stage at which oceans and seas form a feature of its landscape, and an impediment to subjugation of its surface in its entirety. What once were ocean beds have become ocean bottoms, devoid of that which originally filled them. That the process of parting with a watery envelope is an inevitable concomitant of the evolution of a planet from chaos to world, we do not have to go so far afield as Mars and the Moon for testimony. Scrutiny reveals as much in the history of our own globe. Two signposts of the past, one geologic, the other paleontologic, point unmistakably in this direction. The geologic guides us the more directly to the goal. Study of the earth's surface reveals the preponderating encroachment of the land upon the sea since both began to be, and demonstrates that, except for local losses, the oceans have been contracting in size from archaic times. So much is evidenced by the successive places upon which marine beds have been laid down. This suggests itself at once as a theoretic probability to one considering the matter from a cosmic standpoint, and it is therefore the more interesting and conclusive that from an entirely different departure point it should have been one of the pet propositions of the late Professor Dana, who worked out conclusively the problem for North America and published charts detailing the progressive making of that continent. So telling is this reclaiming by nature of land from the sea that it will be well to follow Dana a little into detail, as the details show effectively the continuity of the process acting through eons of geologic time. At the beginning of the Archean age, or in other words, at the epoch when stratified beds were first laid down, the earth reached a turning point in its history. Erosion, superficial and subaerial, then set in to help restrict the domain of the sea. At this juncture, North America consisted of a sickle of terrain enclosing Hudson's Bay and coming down at its apex to a point not much removed from where Ottawa now stands, in about latitude 45 degrees, a Labradorian North America only. This, the kernel of the future continent, curiously symbolized the form that continent was later to take, for its eastern edge was roughly parallel to the present Atlantic coastline, although much within and to the north of it, while its western one was similarly aligned afar off to the now Pacific slope. Besides this continent proper, the Appalachian, Rocky Mountain, Sierra Nevada and Sierra Madre chains stood out of the ocean in long narrow ridges of detached land, outlining in skeleton the bones of the continent that was to be. The Black Hills of Dakota and other highlands made here and there islets in the sea. Much the same backbone showing of continents yet to be filled out was true of Europe, Asia and South America. In Europe the northern countries constituted all that could be called continental land. Most of Norway, Sweden, Finland, Lapland existed then, while the northern half of Scotland, the Outer Hebrides, portions of Ireland, England, France and Germany stood out as detached islands. From this, which is a fair sample of the proportion of land then to land now over the other continents, so far as they are geologically known, we turn to consider more in detail the history of North America. By the time the Upper Silurian period came in, the Appalachian highlands there had been greatly extended and joined to the Labradorian mainland by continuous territory. Otherwise no important addition had occurred, though islands emerged in Ohio, Kentucky and Missouri. At the commencement of the Carbonic era, what are now the Middle States had begun to fill up from the north, and Newfoundland, from a small island in the Upper Silurian, had become a great promontory of Labrador, while the Eastern States region and Nova Scotia had risen into being. The movements closing Paleozoic time upheaved from low islands the Appalachian chain. The earth's crust here crumpled by contraction upon itself, and the movement ended, as Dana says, by making dry land of the whole eastern half of the continent along substantially its present lines. Mesozoic time was the period of the making of the West. It was an era of deposition and coincident subsidence, when the western land had its nose just above water at one moment to be submerged the next. Though on the whole this part of the continent was emerging, the fact was that, synchronously with the sinking of the sea, much of the land from time to time sank too. The contraction which raised the Appalachian Mountains at the beginning of the period, and that of the Rockies at its close, overdid the necessities of the case and caused subsidence elsewhere. The southeastern portion of the continent suffered most, the west on the whole materially gaining. In the Triassic and Jurassic eras the gain was pronounced. It occurred in the Cretaceous also, but with much alternation of loss. Finally, at the close of the Cretaceous, the continent, except for a prolonged Gulf of Mexico and vast internal lakes, was substantially complete. The filling up of these lakes and the reclaiming of land from the Gulf of Mexico constituted the land-making work of tertiary times. The extent of the lakes in the Eocene era is held to show that the general level of the mountain plateau was low and rose later, so that the gain by the land at this time was greater than the map allows to appear. By the beginning of the Quaternary epoch, the continents had assumed their present general area, and since then their internal features have alone suffered change. A similar rising from the sea fell to the lot of Europe, though it has not been detailed with so much care. The skeleton of that continent was at the beginning of depository time much what it is today, but a great inland sea occupied the centre of it, which, as time went on, was gradually silted in and evaporated away, notably during the Upper Silurian period. From all this it is pretty clear that, side by side with alternating risings and sinkings of the land, there was a tolerably steady gain in the contest by which dry ground dispossessed the sea. We may of course credit this to a general deepening of the ocean bottoms due to crumpling of the crust, but we may also impute it to a loss of water, and that the latter is, at least for a part, in the explanation the condition of the Moon and Mars makes probable. Paleontology has the same story of reclamation to tell as geology, and with as much certainty, though its evidence is circumstantial instead of direct, and speaks for the growing importance of the land in the globe's economy since the beginning of depository time, and thus inferentially to its increasing extent. Fossil remains of the plants and creatures that have one after the other inhabited the earth show that the land has been steadily rising both in floral and faunal estimation as a habitat for the earliest ages to the present day. The record lies imprinted in the strata consecutively laid down, and except for gaps, reads as directly on in bettering domicile as in evolutionary development. In Archean times, we find no undisputed evidence of life, either vegetal or animal, but beds of graphite and of limestone point to the possible existence of both. Even anthracite has been found in Archean rocks in Norway and also in Rhode Island. Whether Dawson's Eozoan canadense be a rhizopod or a crystal, doctors of science disagree. Dana, while admitting nothing specific, deems it antecedently probable that algae and later microscopic fungi related to bacteria existed then, living in water well up toward the boiling point. Indeed, it is practically certain that invertebrate life existed because of its already well-developed character in the next era. The lie candidating is inferable for the whole record of the rocks. Relatively, their history is undoubtedly fairly accurate, but absolutely it must be shifted bodily backward into the next preceding era to correspond with fact not yet unearthed. In the Lower Cambrian, when first the existence of life becomes a certainty, that life, so far as known, was wholly invertebrate and wholly marine. Rhizopods, probably, sponges and corals, echinoderms, worms, brachiopods, mollusks, and crustaceans grew amid primitive seaweed and have left their houses in the shape of shells while perishing themselves. Their tracks, too, have thus survived. The trilobites, crustaceans somewhat resembling our horseshoe crab, were the lords of the Cambrian seas, and marked the point to which organic evolution had then attained. Their aquatic character, as well as their simple type, is shown by their thoracic legs having each a natatory appendage. In the next era, the Lower Silurian, the fauna and flora were still marine, although of a higher order than before, and in the Trenton period, the upper part of the era, the earliest vertebrates, fishes, came upon the scene, ganoids and possibly sharks. Nothing terrestrial of this period has yet with certainty been unearthed in America. Europe would seem to have either been more advanced then or better studied since, for there the first plant higher than a seaweed has been dug up, one of a freshwater genus, betokening the land, while in keeping with this, the first insect, an hemipter, also has been disinterred. Both the geography and the life of the Eopaleozoic period, Dana styles Thalassic. Neopaleozoic time, beginning with the Upper Silurian, marked the emergence of the continents, and following them the emergence of life from the water onto this land. In the lower beds of the Upper Silurian in America, we find only the aquatic forms of previous strata, but in a higher one we come in marshes upon plants related to the equiseta or horsetails. In England, land plants appear for the first time in these latest Silurian beds, and in the schists of Angers have been preserved ferns. In both the Old World and New, fossil fishes are found, and the oldest terrestrial species of scorpions, but the great bulk of forms were still marine, corals, crinoids, brachiopods, trilobites, constituting the principal inhabitants. At this time the seas were warm, having much the same temperature, between 65 degrees and 80 degrees north, as between 30 degrees and 45 degrees, the prevalence of a general temperate tropicality being shown by the fact that the common tropical chain corals lived in latitude 82 degrees north. In the Devonian era, the old red sandstone, fishes grew and multiplied, increasing in size apparently through the era, and in the last period of it reaching their culminating point. These pelagic vertebrates much surpassed in structure the terrestrial population of the time, which was of a low type and consisted of invertebrates, such as myriapods, spiders, scorpions, and insects, for the land was only making. In the mid-Devonian, forests of a primitive kind covered such country as there was, an amphibious land composed of jungles and widespread marshes. Tree ferns made the bulk of the vegetation, but among them grew also cycads and yews. Mammoth mayflies flitted through the gloom of these old forests, but no vertebrate as yet had left the sea. Following upon the old red sandstone were laid down the carbonic strata, and with the carbonic entered upon the scene the advanced scouts of an army of progress, evolutionarily impelled to spy out the land, the first amphibians. They made their debut in the sub-Carboniferous section of the era, the oldest of the three periods into which the carbonic is divided, crawling out of the sea to return again, and leaving but footprints at first on the sands of time. In the second period, the coal measures proper, they ventured so far as to leave their skeletons on terra firma, or rather infirma, while their tracks there show them to have been now in great numbers. In this manner the ancestors of the oldest land inhabitants began to struggle out of the sea. In the Permian, the third and latest period of Paleozoic times, we find their descendants established in their new habitat, for in it we come upon the first reptiles. Such possession marks a distinct set-up in function, as in fact, for while amphibians visited dry land, reptiles made it their home. The getting out of the water had now, in the case of the more evolved forms, become an accomplished fact. The reptiles were, indeed, the lowest and most generalized of their class, rhynchocephalians, beak-headed species that by their teeth proclaim their marine origin and their relationship to the great amphibians that still felt undecided where to stay. Meanwhile, in Europe, dragonflies 2 feet across possessed the air, while amphibians there, as here, ancestrally preceded reptiles in occupying the land. Mesozoic times were, par excellence, the age of monsters. For the Triassic, the new red sandstone, Jurassic and Cretaceous eras marked the reign of the reptiles. Great dinosaurs sleep still in the Triassic strata of the Atlantic border and in the Jurassic of the western states, to be unearthed from time to time and given more severe in our museums. Gigantic they were, and very literally possessed the earth. In Europe, they were substantially as in America during these Mesozoic eras, and showed their dominance by long survival in time as well as worldwide distribution in space, for they lived all the way from Kansas to New Zealand, and from the Trias to the Upper Cretaceous. It is supposed by Professor Osborn that many of them, like the herbivorous Brontosaurus, waded in marshes, not wholly unlike in habit to the modern hippopotamus. Others were land-stalking carnivores, like the megalosaurs of a little later date, of enormous size. The largest exceeded any animal which has ever lived, the whales alone excepted. The biggest, the Atlantosaurus and the Brontosaurus, reached a length of 60 feet. For all their bulk, they had scant brains, just enough to enable them to feed and wallow, probably. It is interesting to note that many of the reptiles, the less adventurous, apparently reverted to the sea. For though the crocodilians existed already in the Trias, the plesiosaurians did not come in till the Middle Trias in Europe, and the sea serpents, Mosasaurus, till the Upper Cretaceous. Though dinosaurs dominated life in those days, higher forms, their descendants, unnoticed were gradually creeping in, eventually to supplant them. For brain was making its way unobtrusively in the earliest of the mammals, diminutive creatures at first and of the lowest type, first appearing in the Trias as something approaching the missing link between reptiles and mammals. They later developed into monotremes and marsupials, not rising in differentiation above the latter order to the end of the Mesozoic times, and this both in the Old World and the New. In the Jurassic, too, flying lizards and the first birds appeared, showing their pedigree in their teeth. With Cenozoic times, we come upon the first true or placental mammals, with their culmination up to the date in man. In the Eocene, they were of a primitive type. They were also of a comprehensive one, fitted to eat anything. From this they specialized, some evolving, and some on the whole devolving. The whale, for instance, taking to the water in the Eocene, through the same degenerative proclivity that had characterized the sea saurians ages before. The earth was growing colder, though still fairly warm, and with the fall in temperature, the higher types of life antithetically rose, evolution gradually fitting them to cope with more advanced conditions. In this manner did the land supplant the sea as the essential feature of the earth's surface, first in coming into being, and then by offering conditions fraught with greater possibilities as the habitat of the most advanced forms of life, both plants and animals. The possibility of advance in evolution was largely due to the fact that the land did thus supplant the sea. Spontaneous variation, the as yet unexplained primum mobile in the genesis of species, is probably to be referred to chemism, and is likely later to receive its solution at the hands of that science. In the meanwhile it is evident that unless the variation obtain encouragement from the environment, no advance in type occurs. Now the land offers to an organism sufficiently evolved to benefit by it opportunities the sea does not possess. First of these, undoubtedly, is the care it enables to be given to the young. To cast one's brood upon the waters is not the best method of ensuring its bringing up. There is too much of the uncertainties of wave and current to make the process a healthy one, and even when attached to rocks and seaweed, the attachment to a mother is to be preferred. Without a period of infancy, when the young is enabled to do for itself, no great development is possible. In the only striking exception, the case of the whales, dolphins, and porpoises, size has probably counted for much in the matter, while the development of the cetaceans is far behind that of the majority of land mammals. Change of place, not in distance, but in variety, is another factor. The sea is same as a habitat, 1 square mile of it being much like another, except for gradually changing temperature. The land, on the other hand, from its accidented surface, presents all manner of diversity in the conditions. And the more varied the conditions to which the organism is exposed, the greater its own complexity must be to enable it to meet them. That the terrestrial stage of planetary development is subsequent to the terraquaceous one, and must of necessity succeed it if the latter ever exist on a body, follows from the loss of internal heat on the one hand and from the kinetic theory of gases on the other. To which of the two to attribute the lion's share in the business is matter for doubt, but that both must be concerned in it we may take for certain. So long as the internal heat suffices to keep the body fluid, the liquid itself sees to it that all interstices are filled. As the heat dissipates, the body begins to solidify, starting with the crust. For cosmic purposes it undoubtedly still remains plastic, but cracks of relatively small size are both formed and persist. Into these the surface water seeps. With continued refrigeration, the crust thickens, more cracks are opened, and more water given lodgment within, to the impoverishment of the seas. The process would continue till the pressure of the crust itself rendered plastic all that lay below, beyond which, of course, no fissures could be formed. How competent to swallow all the seas such earth cuticle cracks maybe we ignore, for we cannot be said to know much of the process. We can only infer that to a certain extent internal absorption of surface seas must mark a stage of the evolution by which a star becomes a world, and then an inert mass, one of the dark bodies of which space is full. Of the other means we know more. We are certain that it must take place, though we are in doubt as to the amount it has already accomplished. This method of depletion is by the departure of the water in the form of gas, in consequence of the molecular motions. If we knew the temperature and the age of Mars, and also the amount of atmosphere originally surrounding it, we could possibly predicate its state. Reversely, we can infer something as to age and temperature from its present condition. End of section 13. Reading by Florence.
Section 14 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Daniel Lee. Mars and its Canals by Percival Lowell. Chapter 13. The reddish ochre tracts. Both for their evidence and their extent, the great ochre stretches of the disk claim attention first. Largely unchangeable, these show essentially the same day after day and from the year's beginning to its end. In hue they range from sand color to a brick red, some parts of the planet being given to the one tint, some to the other. It is to the latter that the fiery tint of Mars to the naked eye is due. The differences in complexion are local and peculiar, both in place and time. For though saffron best paints the greater part of the light areas, certain localities present at times a red like that of our red sandstone. Hellas is one of these ruddy regions, and Area another. It is only on occasion that they thus show, and to what to assign their variability is as yet matter of conjecture. Possibly it is owing to Martian meteorologic condition, possibly to something else. But whatever its origin, the change is not so much contradictory of as supplementary to the general fact of unalterableness, which is, after all, the basic trait about them and the keynote to their condition. Land the ochre regions have generally been taken for, and land they still make good their claim to be considered. For the better they are seen, the greater ground for the belief. Indeed, they seem to be nothing but ground, or, in other words, deserts. Their color first points them out for such. The pale salmon hue, which best reproduces in drawings the general tint of their surface, is that which our own deserts wear. The Sahara has this look. Still more, it finds its counterpart in the far aspect of the painted desert of northern Arizona. To one standing on the summit of the San Francisco peaks, and gazing off from that isolated height upon this other isolation of aridity, the resemblance of its lambent saffron to the telescopic tints of the Martian globe is strikingly impressive. Far forest, and still farther desert, are transmuted by distance into mere washes of color, the one robin eggs blue, the other roseate ochre, and so bathed, both in the flood of sunshine from out a cloudless burnished sky, that their tints rival those of fire opal. None otherwise do the Martian colors stand out upon the disk at the far end of the journey down the telescope's tube. Even in its mottlings the one expanse recalls the other. To the painted desert its predominated tint is given by the new red sandstone of the Trias, the stratum here exposed, and this shows in all its pristine nakedness because of the lack of water to clothe it with any but the sparsest growth. Limestones that crop out beside it are lighter yellow, whitish, and steel gray, and seen near give the terrain the look of a painter's palette. Seen from far, they have rather the tint of sand, and the one effect, like the other, is Martian in look. And as if to assimilate the two planetary appearances the more, the thread of blue-green that attention traces athwart the painted desert marks the line of cottonwoods along the banks of the little Colorado River, deserts both, if look be any guarantee of character, with verdure banding them. In other ways these earthly deserts offer a parallel to the Martian. No desert on earth is absolutely devoid of life of some kind, vegetal and animal. The worst conditioned are not what one is taught in childhood to believe a desert to be, a vast waste of sand, with a camel and a palm thrown in to heighten the sterility. In all Saharas outside of the pages of the school books, some vegetation grows, though it is commonly not of a kind to boast of, being rather a succès d'estime, as sagebrush, cacti, and the like. But what is of interest here in the connection is its color, for it is commonly of a more ochreish tint than usual, in keeping with its surroundings, a paling out of the green to something more tawny, indicating a relative reduction of the chlorophyll and an increase of the lipochromes in the tissue of the plant, since the one gives the green tint to the leaves, the other the yellow. As this vegetation, poor as it is, has its annual history, it must alter the look of the desert at times, and produce precisely those slight variations in tint observable on Mars in like circumstance. The Arizona desert dates from no further back than early tertiary times, as the limestone of the Cretaceous there present shows. Water then stretched where the desert is now, and the limestone beds were laid down in it. How old the Martian Saharas are we have no means of knowing. But one thing we may predicate about both. A desert is not an original, but an acquired condition of a planet's surface, demonstrably so in the case of a planet which has had a sedimentary epoch in its life history. In the Arizona desert the surface is composed of depositary rock of Mesozoic times, except where lava streams have flowed down over it since then. The land then was once under water and cannot have been fertile for some time after it emerged. But we're not left to inference in the matter, however good that inference may be. A little to the south of the Painted Desert, in the midst of the barren plateau of northern Arizona, of which the former makes a part, stand the remains of a petrified forest. Huge chalcedony trunks of trees, so savingly transmuted into stone that their genus is still decipherable, lie scattered here over the barren ground in waste profusion, one of them still spanning a canyon, just as it fell in that, to wit, destructive day of a far prehistoric past. The rock stratum on which their remains lie is of Triassic and Cretaceous times, and the petrifications show that in the Cretaceous a stately forest overspread the land. In those days, at least, the spot was fertile, where now sparse sagebrush and cacti find a living hard. Not here alone, where the blocks are so conspicuous as to invite their carrying away, is a former flourishing growth of vegetation attested, but over large adjoining areas of desert search has brought the like past tendency to light. Fragments of what were once trees have been picked up in the Little Colorado Basin, and in the neighborhood of Ash Fork, on both sides, that is, of the present forest crown that covers the higher part of the plateau from which rise the San Francisco peaks. In the blue distance, the mountains look down verdure-clad upon a now encircling waste, but one which in earlier eras was as pine-bearing as they. Their lofty oasis is all that is now left of a once fertile country. The retreat of the trees up the slopes in consequence of a diminishing rainfall, until a rise of 2,000 feet from what once was timberland, is necessary to reach the tree line of today, being typical of desert lands, and testifying to greater aqueous affluence in the past. In the same manner, streams descend from the cedar-clad range of the Lebanon to lose themselves in the Arabian desert, just without the doors of Damascus, and Palestine is desiccated within history times. Palestine, a land once flowing with milk and honey, can hardly flow poor water now, and furnishes another straw to mark the ebbing of the water supply. This making of deserts is not a sporadic, incidental, or local matter, although local causes have abetted or hindered it. On the contrary, it is an inevitable result of planetary evolution, a phase of that evolution which follows from what has been said in Chapter 7 on the abandonment of a planet by its water. Deserts are simply another sign of the same process. The very aging which began by depriving a body of its seas takes from it later its forest and its grass. A growing scarcity of water is bound to depauperate the one, as it depletes the other. We have positive proof of the action in our own deserts, for these bear testimony, in places at least, to not having always been so, but to have gradually become so within relatively recent times. But we have more general proof of the action from the position occupied on the earth's surface by its deserts. The significant fact about the desert making so stealthily going on is that only certain zones of the earth's surface are affected. Those belting the two tropics of Cancer and Capricorn, for several degrees on either side of them, most exhibit the phenomenon. Such positioning of the deserts is not due to chance. Directly, of course, desertism is due to the dearth of rain. This, in turn, depends on the character and condition of the winds. If a wind laden with moisture travel into a colder region of the globe, its moisture is precipitated in rain, and we have a fertile country. If it voyage into a warmer clime, it takes up what little moisture may be there already, and a desert is the result. Now our system of winds is such as to produce a fall of rain for the different latitudes, as tabulated by Seppan, thus. Zone 1, 40 degrees north to 27 degrees north. Little rain in summer, but much in winter. Zone 2, 27 degrees north to 19 north. Little rain at all seasons. Zone 3, 19 degrees north to 7 degrees north. Little rain in winter, but much in summer. Zone 4, 7 degrees north to 1 degree north. Abundant rain at all seasons. Zone 5, 1 degree north to 17 degrees south. Little rain in winter, but much in summer. Zone 6, 7 degrees south to 30 degrees south. Little rain at all seasons. Zone 7, 30 degrees south to 35 degrees south. Little rain in summer, but much in winter. Zones 2 and 6, the zones of minimal rainfall, are also those in which the deserts occur. The northern one traverses Southern California, Arizona, New Mexico, the Sahara, Arabia, and the Desert of Gobi. The southern, Peru, the South African Veldt, and Central Australia. The belts are wavy bands which by their form betray both a general underlying trend to drought at these parallels and also the effect of local topography in the matter. From being distributed thus in belts, it is evident that the deserts are general globe phenomena, and from their being found in only the zones of least rainfall that the earth has itself entered through, though not far as yet, upon the desert stage of its history. Once begun, the desert areas must perforce spread as water becomes scarce, invading and occupying territory in proportion as the rainfall there grows small. Now the axial tilt of Mars is almost exactly the same as that of our Earth, the latest determinations from the ensemble of measures giving 24 degrees for it. Here then we have initial conditions reproducing those of Earth. But from the smaller size of the planet that body would age the earlier, since it would lose its internal heat the more rapidly, just as a small stone cools sooner than a larger one. On general principles, therefore, it should now be more advanced in its planetary career. In consequence, desertism should have overtaken more of its surface than has yet happened on Earth, and instead of narrow belts of sterility, we should expect to find there Saharas of relatively vast extent. Now such a state of things is precisely what the telescope reveals. The ochre tracts occupy 9/10 of the northern hemisphere, and 1/3 of the southern. 3/5, therefore, of the whole surface of the planet is a desert. Of cosmic as well as of particular import is the correlation thus made evident between the physical principles that affect the aging of a planet and the aspect Mars presents. Experimental corroboration of those laws is thus afforded, while reversely, confidence in their applicability is increased. With continued observation, the planet appears more desiccate as improved conditions bring it nearer. Dry land, as it was thought to be, proves even drier, something which lacks water for the ordinary necessities of a living world. The picture the planet offers to us is thus arid beyond present analog on Earth. Pitiless as our deserts are, they are but faint forecasts of the state of things existent on Mars at the present time. Only those who as travelers have had experience of our own Saharas can adequately picture what Mars is like and what so waterless a condition means. Only such can understand what is implied in having the local and avoidable thus extended into the unescapable and the worldwide, and what a terrible significance for everything Martian lies in that single word, desert.
End of section 14.
Section 15 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Montes, Las Cruces, New Mexico. Mars and its Canals by Percival Lowell. Chapter 14. Summary. If now we review with the mind's eye the several features of Mars which we have surveyed with the bodily one, we shall be surprised to find to what they commit us. Suggestive as each is considered by itself, the ensemble into which they combine proves of multiplicate force in its implication. for each turns out to fit into place in one consistent whole, a scheme of things in which are present all the conditions necessary to the existence and continuance of those processes which constitute what we call life. In short, we are conducted with a cogency which grows as we consider it to the conclusion that Mars is habitable. Two ways of appreciating this cogency are open to us. We may treat it with the simple reasoning of common sense, as we should a dissected map or a piece of machinery in which we realize we are right when the several parts at last fit together and the picture stands revealed or the machine works. Or we may subject the evidence to quantitative estimates for and against by the doctrine of probabilities, and thus evaluate the chances of its being correct. Consciously or unconsciously, this is what we are about in our decisions every day of our lives. At the one end of the line are those skillful judgments where the balance is so keen-edged that the least overweight on one side dips the scales to a conclusion. At the other extremity stand those deductions which we usually speak of as proved, such as the law of gravitation. But both assurances rest really upon probability and differ only in degree. What we mean by proof of anything is that a supposition advanced to account for it explains all the facts and is not opposed to any of them, and that the balance of probability, in consequence, is very largely in its favor. Now, if several pieces of evidence, distinct in their origin, concur to a given conclusion, the probability that that conclusion is correct is far greater than what results from each alone, and mounts up soon to something much exceeding what bettors at races call certainty odds. However unversed the average man may be in calculating the probability, he recognizes the fact in his dealings with his fellows by the way he attaches weight to concurrent testimony. It is such concurrent evidence that we have now to consider. To this end, we will marshal the several facts ascertained in a summarized list for their easier intercomparison. These facts are: 1. Mars turns on its axis in 24 hours, 37 minutes, 22.65 seconds, with reference to the stars, and in 24 hours, 39 minutes, 35.0 seconds as a mean, with regard to the sun. Its day, therefore, is only about 40 minutes longer than ours. 2. Its axis is tilted to the plane of its orbit by about 23 degrees, 59 minutes, most recent determination, 1905. This gives the planet seasons almost the counterpart of our own in character, but in length nearly double ours. 4. 3. Its year consists of 687 of our days, 669 of its own. 4. Polar caps are plainly visible which melt in the Martian summer to form again in the Martian winter, thus implying the presence of a substance deposited by cold. 5. As the polar caps melt, they are bordered by a blue belt, which retreats with them. This excludes the possibility of their being formed of carbon dioxide, and shows that of all the substances we know, the material composing them must be water. 6. In the case of the southern cap, the blue belt has widenings in its places. These occur where the blue-green areas bordering upon the polar cap are the largest. 7. The extensive shrinkage of the polar snows shows their quantity to be inconsiderable, and points to scanty deposition due to dearth of water. 8. The melting takes place locally after the same general order and method, Martian year after year, both in the south cap, 9, and in the north one. This is evidenced by the recurrence of rifts in the same places annually in each. The water thus let loose can therefore be locally counted on. 10. That the south polar cap is given to greater extremes than the north one implies again, in view of the eccentricity of the orbit and the tilt of the axis, that deposition in both caps is light. 11. The polar seas at the edges of the caps being temporary affairs, the water from them must be fresh. 12. The melting of the caps on the one hand and their reforming on the other affirm the presence of water vapor in the Martian atmosphere, of whatever else that air consists. 13. Since water vapor is present, of which the molecular weight is 18, it follows from the kinetic theory of gases that nitrogen, oxygen, and carbonic acid of molecular weights 28, 32, and 38 respectively are probably there too, owing to being heavier. 14. The limelight bears testimony to this atmosphere. 15. The planet's low albedo points to a density for the atmosphere very much less than our own. 16. The apparent evidence of twilight goes to confirm this. 17. Permanent markings show upon the disk, proving that the surface itself is visible. 18. Outside of the polar cap, the disk is divided into red ochre and blue-green regions. The red ochre stretches have the same appearance as our deserts seen from afar. 19. And behave as such, being but little affected by change. 20. The blue-green areas were once thought to be seas, but they cannot be such because they change in tint according to the Martian season, and the area and amount of the lightening is not offset at the time by corresponding darkening elsewhere. 21. Nor by any augmentation of the other polar cap or precipitation into cloud. It cannot therefore be due to shift of substance. 22. Therefore, they are all seamed by lines and spots darker than themselves, which are permanent in place, so that there can be no bodies of water on the planet. 23. On the other hand, their color, blue-green, is that of vegetation. This regularly fades out, as vegetation would, to ochre for the most part, but in places changes to a chocolate brown. 24. The change that comes over them is seasonal in period, as that of vegetation would be. 25. Each hemisphere undergoes this metamorphosis in turn. 26. That it is recurrent is again proof positive of an atmosphere. 27. The changes are metabolic, since those in one direction are later reversed to restoration of the original status. Anabolic as well as catabolic processes thus go on there. That is, growth as well as decay takes place. This proves them of vegetal origin. 28. The existence of vegetation shows that carbonic acid, oxygen, and undoubtedly nitrogen are present in the Martian atmosphere, since plants give out oxygen and take in carbonic acid. 29. The changes in the dark areas follow upon the melting of the polar caps, not occurring until after that melting is underway. 30. And not immediately then, but only after the lapse of a certain time. 31. Though not seized now, from their look the dark areas suggest old sea bottoms, and when on the terminator appear as depressions, whether because really at a lower level or because of less illumination is not certain. 32. That they are now the parts of the planet that support vegetation hints the same past office, as water would naturally drain into them. That such a metamorphosis should occur with planetary aging is in keeping with the kinetic theory of gases. 33. Terminator observations prove conclusively that there are no mountains on Mars, but that the surface is surprisingly flat. 34. But they do reveal clouds which are usually rare and are often, if not always, dust storms. 35. White spots are occasionally visible, lasting unchanged for weeks, in the tropic and temperate regions, showing that the climate is apparently cold. 36. But at the same time proving that most of the surface has a temperature above the freezing point. 37. In winter, the temperate zones are more or less covered by a whitish veil, which may be hoarfrost or may be cloud. 38. A spring haze surrounds the North Polar Cap during the weeks that follow its most extensive melting. 39. Otherwise, the Martian sky is perfectly clear, like that of a dry and desert land. The way in which these 39 articles fit into one another to a mortised whole is striking enough at first sight, but becomes more and more impressive the more one considers it. For some are due to one kind of observation, some to another. In the taking they are unrelated, yet in the result they agree. Equally pregnant is the history of their acquisition. Most of them were detected as the outcome of observations at the opposition of 1894, and led to the theory which was published in the writer's first book on the subject. Others are the result of the 5 oppositions that have since occurred. These have proved entirely corroborative of the previous ones and of the theory then deduced, and that in 2 distinct ways. First, by the accumulated evidence they have brought to the matter along the old lines, and secondly, by what they have revealed in new directions. Of these 39 articles of Martian scientific faith in observation or deduction, 9, 10, 21, 22, 25, 27, 28, 30, 33, 35, 36, and 38 are in whole or part new. That continued scrutiny is thus corroborative of the earlier results, both along the old and along new lines of investigation, warrants additional confidence in the conclusion. Considering now these counts, we see that they are reasonably evident on Mars the presence of 1. Days and seasons substantially like our own. 2. An atmosphere containing water vapor, carbonic acid, and oxygen. 3. Water in great scarcity. 4. A temperature colder than ours, but above the Fahrenheit freezing point, except in winter and in the extreme polar regions. 5. Vegetation. First and foremost of these is air. In order to make it possible for vital processes of any sort to take place, the body of a planet must be clothed with an atmosphere. By the modesty of nature, the old astronomers would have said. Such a covering subserves 2 purposes. It keeps out the cold of space, thus permitting the maintenance of a temperature sufficient to support life, and it affords a medium through which metabolism can go on. Now, the presence of air is attested first and foremost by the fact of change in the Martian markings, 12, 13, 26, 28, and 35. The changes observed are conspicuous, are both inorganic in the case of the polar caps 12, 13, and 35, and metabolic or organic 26 and 28 in the case of the blue-green areas. That is, they consist of building up as well as of pulling down, and are planet-wide in occurrence. Such changes could not occur in the absence of an atmosphere. They show that this atmosphere consists of water vapor 5, carbonic acid, and oxygen 28. The limelight, the apparent evidence of a twilight arc, and the planet's low albedo indicate that this atmosphere is thin. The appearance of the surface, 35, suggests cold, indicative again of a thin air. Such tenuity is in accord with what a priori principles would lead us to expect, and tends to show that reliance on general principles is here not misplaced, a point of some interest. Lastly, the occurrence of clouds, 34, visibly floating and traveling over the surface and Hayes at times, 38, proves in another way the existence of the medium in which alone this could be possible. Water is the next substance vital to planetary life. As to its actual presence, the polar caps 4 through 12 have most to say. As to its relative absence, the rest of the disk, 17 through 22. The forthright conception of the polar caps as composed of snow and ice is borne out by further investigation into what could cause the observed phenomenon. Carbonic acid, the only other substance we know capable in any way of resembling what we see, turns out not capable of producing one important detail of the caps' appearance, the blue band, 5, which accompanies them in their retreat. Water alone could do this. The melting of the caps shows that water vapor must be a constituent of the Martian atmosphere. Moreover, as the molecular weight of the water vapor is less than that of oxygen or nitrogen or carbon dioxide, if the former can exist in the atmosphere of the planet, a fortiori, must these other gases. So that from this we have knowledge of the possibility of the presence of oxygen, nitrogen, and carbon dioxide there. From 28, we saw that their actual existence is demonstrated. The next step is the ascertainment that the water is in very small amount. The extensive melting of the caps, 7, shows that their quantity to be inconsiderable, which is the first fact pointing to a dearth of water. The second comes from the aspect and behavior of the reddish ochre regions, which proclaim them deserts, 18 and 19. The third from the detection of the character of the blue-green areas as not seas, 20, 21, and 22. In several different ways, study of these regions asserts their non-aquatic constitution, the easiest to appreciate being that they are traversed by permanent dark lines and other equally sedentary markings, 22. No bodies of water, therefore, are to be seen outside the ephemeral polar seas immediately surrounding the caps as they melt. This leads us to the third presence on Mars indicative of a living world, vegetation. The other two spoke of substances necessary to life. The premises in the case. This one of organic existence itself, its conclusion. The evidence consists of static testimony from the look of the blue-green areas, 23, and of kinematic derived from their behavior, 24, 25, 26, and 27. Vegetation would present exactly the appearance shown by them, and nothing that we know of but vegetation could. But, suggestive as their appearance is, it is as nothing compared with the cogent telltale character of their behavior. The seasonal change that sweeps over them is metabolic, constructive as well as destructive, that is, and proclaims an organic constitution for them such as only vegetation could produce. In tint, their metamorphoses are those of the same substance, for the blue-green lapses into ochre and revives again to blue-green, just as vegetation does on our own earth at the proper season of the year, taking both the sun and the advent of water into reckoning. Furthermore, certain of the large dark areas turn to a chocolate brown at times, which is the color of fallow ground and suggestive, at least, as occurring where the blue-green at other seasons is the most pronounced. Lastly, the change occurs at the epoch at which, from a knowledge of the melting of the polar caps, theory demonstrates that it ought to take place as if it be due to the action of vegetation. That this was the case was evident from much less information than is forthcoming today. But what is significant, each new fact discovered about the planet goes to show that it is unquestionably true. End of section 15. Recording by Edward Montes, Las Cruces, New Mexico.
Section 16 of Mars and its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michael Knowles, Fort Worth, Texas. Mars and its Canals by Percival Lowell, Part 2, Non-Natural Features, Chapter 15, The Canals. From the detection of the main markings that diversify the surface of Mars, we now pass to a discovery of so unprecedented a character that the scientific world was at first loath to accept it. Only persistent corroboration has finally broken down distrust, and, even so, doubt of the genuineness of the phenomenon still lingers in the minds of many who have not themselves seen the sight because of the inherent difficulty of the observations. For it is not one where confirmation may be summoned in the laboratory at will, but one demanding that the watcher should wait upon the sky with more than ordinary acumen. This latter-day revelation is the discovery of the Canals. Quite unlike in look to the main features of the planet's face is this second set of markings which traverse its disk, and which the genius of Schiaparelli disclosed. Unnatural they may well be deemed, for they are not in the least what one would expect to see. They differ from the first class not in degree but in kind, and the kind is of a wholly unparalleled sort. While the former bear a family resemblance to those of the earth, the latter are peculiar to Mars, finding no counterpart upon the earth at all. Introduction to the mystery came about in this wise, and will be repeated for him who is successful in his search. When a fairly acute-eyed observer sets himself to scan the telescopic disk of the planet in steady air, he will, after noting the dazzling contour of the white polar cap and the sharp outlines of the blue-green seas, of a sudden be made aware of a vision as of a thread stretched somewhere from the blue-green across the orange areas of the disk. Gone as quickly as it came, he will instinctively doubt his own eyesight, and credit to illusion what can so unaccountably disappear. Gaze as hard as he will, no power of his can recall it, when, with the same startling abruptness, the thing stands before his eyes again. Convinced, after 3 or 4 such showings, that the vision is real, he will still be left wondering what and where it was. For so short and sudden are its apparitions that the location of it is dubiously hard. It is gone each time before it has got its bearings. By persistent watch, however, for the best instance of definition, backed by the knowledge of what he is to see, he will find its coming more frequent, more certain, and more detailed. At last, some particularly propitious moment will disclose its relation to well-known points, and its position be assured. First, one such thread, and then another will make its presence evident, and then he will note that each always appears in place. Repetition in situ will convince him that these strange visitations are as real as the main markings, and are as permanent as they. Such is the experience every observer of them has had, and successes depend upon the acuteness of the observer's eye and upon the persistence with which he watches for the best moments in the steadiest air. Certain as persistence is to be rewarded at last, the difficulty inherent in the observations is ordinarily great. Not everybody can see these delicate features at first sight, even when pointed out to them, and to perceive their more minute details takes a trained as well as an acute eye, observing under the best conditions. When so viewed, however, the disk of the planet takes on a most singular appearance. It looks as if it had been cobwebbed all over, suggestive of a spider's web seen against the grass of a spring morning. A mesh of fine reticulated lines overspreads it, which with attention proves to compass the globe from one pole to the other. The chief difference between it and a spider's work is one of size, supplemented by greater complexity, but both are joys of geometric beauty. For the lines are of individually uniform width, of exceeding tenuity, and of great length. These are the Martian canals. 2 stages in the recognition of the reality confront the persevering plotter. First, the perception of the canals at all, and second, the realization of their very definite character. It is wholly due to the lack of suitable conditions that the true form of the Martian lines is usually missed. Given the proper prerequisites of location or of eye, and their pencil-mark peculiarity stands forth unmistakably confessed. It is only where the seeing or the sight is at fault that the canals either fail to show or appear as diffuse streaks, the latter being a halfway revelation between the reality and their not being revealed at all. Much misconception exists on this point. It has been supposed that the improved atmospheric conditions simply amount to bringing the object nearer by permitting greater magnification without altering the hazy look of its detail. Not so. They do much more than this. They steady the object as much as if a page of print from being violently shaken should be suddenly held still. The observer would at once read what before had escaped him for being a blur. So it is with the canals. In reality, pencilings of extreme tenuity, the agitations of our own air spread them into diffuse streaks, an effect of which any one may assure himself by sufficiently rapid motion of a drawing in which they are depicted sharp and distinct, when he will see them take on a streaky look, as the writer has observed them under both aspects, and has seen them pass from the indefinite to the defined as the seeing improved. He has practical proof of the fact, and this not once but an untold number of times. Atmospheric conditions far superior to what are good enough for most astronomic observations are needed for such planetary decipherment, and the observer experienced in the subject eventually learns how all-important this is. Under these conditions, the testimony of his own eyesight upon the character of these markings is definite and complete. And the first trait that then emerges from confusion is that the markings are lines, not simply lines in the sense that any sufficiently narrow and continuous marking may be so called, but lines in the far more precise sense in which geometry uses the term. They are furthermore straight lines. As Schiaparelli said of them, they look to have been laid down by rule and compass. The very marvel of this sight has been its own stumbling block to recognition, joined to the difficulty of its detection. For not only is the average observatory not equipped by nature for the task, but what is not good air often masquerades as such. Trains of airwaves exist at times so fine as to confuse this detail, or even to obliterate it entirely, while at the same time they leave the disk seemingly sharp cut, with the result that one not well versed in such vagaries thinks to see well when in truth he is debarred from seeing at all. When study of the conditions finally ends in putting him upon the right road, the sight that rewards him can hardly be too graphically described. Next to the fact that they are lines, definiteness of direction is the chief of their characteristics to strike the observer. The lines run straight throughout their course. This is absolutely true of 90% of them, and practically so of the remaining 10%, since the latter curve in an equally symmetric manner. Such directness has I know not of what immediate impressiveness. Quite unlike the aspects of the main markings, which show a natural irregularity of outline, these lines offer at the first glance a most unnatural regularity of look. Nothing on earth of natural origin on such a scale bears them analog. Nor does any other planet show the like. They are, in fact, distinctively Martian phenomena. This is the first point in which they differ from the markings we have hitherto described. The others were generic planetary features. These are specific ones peculiar to Mars. Equally striking is the uniform width of each line from its beginning to its end as it stands out there upon the disk. The line varies not in size throughout its course any more than it deviates in direction. It counterfeits a telegraph wire stretched from point to point. Like the latter seen afar, the width, too, is telegraphic, for it is not so much width as want of it that is evident. Breadth is inferable solely from the fact that the line is seen at all, and relative size by difference of insistency. Indeed, the apparent breadth has been steadily contracting as the instrumental, atmospheric, and personal conditions have improved. All three of the factors have conduced to such a maceration, but the middle one the most. For the airwaves spread every marking, and the effect is relatively greatest upon those which are most slender. As the currents of condensation and refraction pulse along, their denser and their thinner portions refract rays on either side of their true place, and thus the same time confuse a marking and broaden it. The consequence is that the better the atmospheric conditions and the more that has been learned about utilizing them, the finer the lines have shown themselves to be. Herein we have a specific intrinsic difference between the fundamental features and the lines. The main markings have extensions in 2 dimensions, the latter in 1. Distinctive as they thus are, they have, in keeping with their appearance, been given a distinctive name, that of canal. Useful as the name is, and, as we shall later see, applicable, it must not be supposed that what we see are such in any simple sense. No observer of them has ever considered them canals dug like the Suez Canal or the Phoenix-like Panama one. This supposition is exclusively of critic creation. Their precise width is not precisable. They show no measurable breadth, and their size, therefore, admits for certain only of an outside limit. They cannot be wider than a determinable maximum, but they may be much less than this. The sole method of estimating their width is by comparison of effect with a wire of known caliber at a known distance. For this purpose, a telegraph wire was stretched against the sky at Flagstaff, and the observers, going back upon the mesa, observed and recorded its appearance as their stations grew remote. It proved surprising at what great distances a slender wire could be made out when thus projected against the sky. The wire in the experiment was only but 0.0726 of an inch in diameter, and yet could be seen with certainty at a distance of 1,800 feet, at which point its diameter subtended only 0.69 of a second of arc. How small this quantity is may be appreciated from its taking more than 90 such lines laid side by side to make a width divisible by the eye. Such slenderness at the distance of Mars would correspond, under the magnification commonly used, only to 3/4 of a mile. Theoretically, then, a line 3/4 of a mile wide there should be visible to us. Practically, both light and definition is lost in the telescope, and it would be nearer to the mark to consider in such case 2 miles as the limit of the perceptible. With a planet nearer than this, as is often the case, the width which could be seen would be proportionally lessened. Perhaps we shall not be far astray if we put 1 mile as the limiting width which could be perceived on Mars at present, with distance at its least and definition at its best. That so minute a quantity should be visible at all is due to the line having a sensible length, and by summation of sensations causing to rise into consciousness what would otherwise be lost. A stimulus too feeble to produce an effect upon a single retinal rod becomes recognizable when many in a row are similarly excited. The experiment furnished another criterion of importance as regards to the supposition that the lines on Mars are illusory. It showed that the brain-begotten impressions of wires that did not exist could be told from the real thing when the wire subtended 0.69 of a second of arc or more. That below this, the outside stimulus was too weak to differ recognizably from the optic effects otherwise produced, while when the real wire was diminished to 0.59, it could not be seen at all. Now, the majority of lines on Mars so far recognized and mapped lie in the strength of impression far above the superior limit of 0.69. To one versed in Martian canal detection, there is no possibility of self-deception in the case, the canals being very much more salient objects to an expert than those who have not seen them suppose. For it must not be imagined that, when one knows what to be on the lookout for, they're the difficult objects they seem to the tyro. Just as the satellites of Mars were easily seen once they were discovered, so with these lines. A mile or 2 we may take, then, with safety, as the smallest width for one of the lines. The greatest was got by comparing what is by far the largest canal, the Nilocertus, with the micrometer thread. From such determination it appeared that this canal was from 25 to 30 miles wide. But it is questionable whether the Nilocertus can properly be termed a canal, so much does it exceed the rest. It is certainly far larger than the majority of them. For comparative estimates between its size and that of the others, 15 to 20 miles for the width of the larger of the Martian canals seems to be the most probable value, and 2 or 3 miles only of the more diminutive of those so far detected. On the other hand, the length of the canals is relatively enormous. With them,
2,000 miles is common, while many exceed 2,500, and the Eumenids Orcus is 3,540 miles from the point where it leaves the Phoenix Lake to the point where it enters the Trivium Charontis. This means much more on Mars than it would on Earth, owing to the smaller size of the planet. Such a length exceeds a third of the whole circumference of its globe at the equator. But what is still more remarkable, throughout the whole of the long course taken by the canal, it swerves neither to the right nor to the left of the great circle joining the 2 points. Of these several peculiarities of the individual canal, it is difficult to know which to allot the palm for oddity: great circle directness, excessive in length, want of width, or striking uniformity. Each is so anomalously unnatural as to have received the approving stamp of incredulity. Yet so much, wonderful as it is encountered on the very threshold of the subject.
End of section 16. Recording by Michael Knowles, Fort Worth, Texas. Section 17 of Mars and Its Canals. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michael Knowles, Fort Worth, Texas. Mars and Its Canals by Percival Lowell. Chapter 16, Their System.
For, outdoing in suggestiveness the individual traits of the lines is the relation shown by them to one another. It is the communal characteristics of the phenomenon that are most surprising. The individual peculiarities of the lines impress themselves at once, the communal only as the result of experience, collation, and thought. As the observer becomes trained, the more lines he is able to make out, until they fairly seem the whole surface of the light areas of the planet. Their name collectively is legion, while to name them individually is fast getting, for the number detected to be impossible. As with the increasing family of asteroids, figures alone will prove adequate to the task. Interdependence, not independence, marks the attitude of the canals. Each not only proceeds with absolute directness from one point to another, but at its terminals it meets canals which have come there with like forthrightness from the other far places upon the planet. Nor is it two only that thus come together at a common junction. 3, 4, 5, up to as many as 14 thus make rendezvous, and it is a poor junction that cannot show at least 6 or 7. The result is a network which triangulates the surface of the planet like a geodetic survey into polygons of all shapes and sizes, the Aryan areolas. The size of the pieces forming this tessellate ground depends solely upon the fineness of the definition. With every increase in the power of seeing, each areola is cut into still smaller portions, usually by connection between its corners. Thus, a polygon or rhombus is split into triangles which may themselves be divided in like manner, the mosaic breaking into bits, the sides of which, however, always remain clean cut. From this arrangement it is at once evident that the canals are not fortuitously placed. That lines should thus meet exactly and in numbers at particular points, and only there, shows that their locating is not the outcome of chance. If very thin rods be thrown haphazard over a surface, the probability that more than 2 will cross at the same point is vanishingly small. Increasingly assured is it that this would not happen generally. The result we see is therefore not a matter of chance, but of some law working to that end. To the detection of what that law is precedes the easier ascertainment of what it is not. The lines, for example, cannot be rivers, which was the first explanation offered of them by Proctor many years ago, because of their peculiar straightness. Nor can they be channels, the name given to them by Schiaparelli, except in the non-committal sense in which he used the term. For here again their geometric regularity is bar to any estuary-like hypothesis. For quite another reason they cannot be cracks because of their uniform size throughout. Their unbroken character is another fatal objection to the same suggestion. For cracks in ground never pursue for any great distance a continuous course, any more than they keep uniform or straight. The state of an old ceiling is a case in point. When it breaks, it does so in fissures that proceed a certain way, then give out to be continued by others roughly parallel to the first, but parted from them. The same character is shown by the rills on the moon. The straight wall, so called, is composed of 3 such sections, and the little rill on the right of it, west of Brit, of 4. Thus they were seen at Flagstaff, and as, to the writer's knowledge, they have not been so depicted elsewhere, the fact may serve to give some idea of the definition there. That the underlying cause is not explosion or contraction is also evidenced by the canals collectively as well as individually. Their arrangement into a system, for cracks, however produced, could only originate from certain centers and could not fit into those starting from others, as the canals invariably do. For each canal goes as undeviatingly to one terminal as it left forthrightly from another. If one wishes to see what explosion or contraction can do, he has only to look at the moon for an opera glass, when he will be shown a very different sight of what the drawings of Mars detail. Thus, just as, considered individually, the lines cannot be watercourses because of their straightness, so they cannot be cracks because of dovetailing into one another. The fact that they form a system shows that whatever caused them operated over the whole planet, linked in cause as an effect throughout each section. This at once negatives any purely physical cause of which we have cognizance. For upon a globe still so subject to physical vicissitude as Mars by its aspect shows itself to be, latitude must tell in the phenomena its zones exhibit. Polar snows that wax and wane speak of Arctic conditions very diverse from temperate and tropic states, and what would affect one could not influence the other. Yet the mesh rises superior to zonal solicitation as to local barrier. It is not something dependent either on the temperament or the complexion of the globe's different parts. It transcends surface restriction and becomes planet-wide in its working. The importance of this omnipresence dilates in meaning as one dwells in thought upon it. Ubiquitous as it is, the mesh which thus covers the Martian surface like a veil spread completely over it is unlike a veil in being irregular in texture. Not only are the interstices of various shape and pattern, but the mesh itself is of locally differing size. Though the threads are straight and uniform throughout, they are not all alike, besides being unsymmetrically interwoven. Some are at least of 10 times the coarseness of others, and from this fact and the Bo-Peep effect of our airwaves, all are not visible at once. In consequence, the network is not so impressive at first glance as it becomes upon a synthesis of the observations. When this is done, the surface proves to be fairly evenly cut up, as recourse to the maps printed in this volume will amply demonstrate. These maps, as on page 31, are made from the result of but one opposition, and at each opposition some zone is in a more canal-showing state than others, owing to the Martian season at the time. A still greater uniformity in canal distribution results from a blending of many. From the completeness of the mesh, it follows that in the course taken severally by the canals, no one direction preponderates over another. Considered by and large, the canals seem to be equally distributed round the compass points, and this at all longitudes and nearly all latitudes. Tropic, temperate, and even Arctic canals show a pleasing impartiality in the manner of the course pursued. The only exceptions occur in the neighborhood of the pole. There a slight tendency may be seen to a north and south setting. Though so much is visible in a general way from the map, it is of interest to go into the subject with more particularity, and to that end to show it statistically. The several canals traversing each zone were therefore counted, and the area of the zone computed. The manner of canal distribution thus found is given in the following table, in the second column of which stand the areas of the several zones upon the planet, each 10 degrees wide. Except the one next to the snow, and, in the third, the number of canals found traversing them, reduced to percentages of the 0 to 10 degree zone. A fourth column shows the total length of the canals in each zone, those from 0 to 20 degrees being taken from the 1896 globe, those from 20 to 90 degrees from the 1903. This is in order to annul the effect of the season upon the showing of the canals as much as possible. Zone 0 to 10 degrees. Area 1. Number of canals weighted 1. Actual length 1. Zone 10 to 20 degrees. Area 0.97. Number of canals weighted 0.89. Actual length 0.91. Zone 20 to 30 degrees. Area 0.91. Number of canals weighted 0.93. Actual length 0.72. Zone 30 to 40 degrees. Area 0.82. Number of canals weighted 0.90. Actual length 0.71. Zone 40 to 50 degrees. Area 0.71. Number of canals weighted 0.78. Actual length 0.66. Zone 50 to 60 degrees. Area 0.58. Number of canals weighted 0.64. Actual length 0.59. Zone 60 to 70 degrees. Area 0.42. Number of canals weighted 0.43. Actual length 0.42. Zone 70 to 80 degrees. Area 0.26. Number of canals weighted 0.30. Actual length 0.34. Zone 80 to 85 degrees. Area 0.07. Number of canals weighted 0.12. Actual length 0.11. The numbers continue fairly non-committal until we begin to approach the pole, when they commence to increase. Much the same result is got if we take the actual canal lengths in each zone, as the fourth column shows. The crowding of the canals poleward is marked. The canals, therefore, are phenomena that stand in peculiar relationship to the polar cap. This corroborates the inference about them due to their running out of the edge of snow. They not only emanate from it, but they do so in numbers surpassing what is elsewhere observable over the disk. Otherwise, it is with their departure points. These are not scattered haphazard over the surface, but bear to its general features definite relations. If we consider the map, obliterating the lines, and then seek to connect the most salient points of the planet's topography by direct avenues of communication, we shall find that our putative lines fall exactly where the real ones occur. For the most part, the real lines emanate from well-marked indentations on the dark regions, fitted by natural position for departure points. What, if these were seas, we should call their most conspicuous bays. They thus leave in the southern hemisphere the deepest folds of the great diaphragm, for the most part, though on occasion they run out of them where they will. From equally conspicuous points in the dark northern areas other lines proceed, while in the center of the continents the canals make for more or less salient spots, small patches of shading like the trivium or the wedge of the Cassius, or simply round black radiants like the Lucy Ismeni. From this it appears that the lines are locally dependent upon the general topography of the fundamental features of the surface. For some reason they connect the very points most suggestive of intercommunication. As from their characteristics it is perfectly evident that the lines are neither rivers nor cracks, it follows that such a communicating habit is of the most telltale character. To be so dissimilar in kind from the main markings, and yet so dependent upon them, hints that their positioning occurred after the formation of the main features themselves. We reach thus from the look of the lines and their location a most striking deduction, that the lines are not coeval with the main markings, but have come into being later and with reference to the general topography of the planet. The network is not only a mesh de facto, then, but one de jure, which, subsequent to the fashioning of the seas and continents and what these have now become, has been superposed upon them.
End of section 17. Recording by Michael Knowles, Fort Worth, Texas.